Welcome to Stellar Worlds. Did you know that beyond our home planet, there are trillions of fascinating worlds waiting to be discovered? From scorching hot giants of liquid metal to icy realms with deep oceans and potentially even havens for life, each exoplanet tells a unique story. Join us as we dive into the most intriguing planets in the universe, right here on Stellar Worlds. Let's explore the universe together. Are you ready? Let's begin. For our first world today, we're warping on over to WASP 132b, the hot Jupiter that reveals secrets of gas giant evolution. We're going on a journey 1,200 light years from Earth to explore one of the most fascinating worlds ever discovered. A planet so hot it glows, so massive it makes Jupiter look small, and so close to its star that it completes an orbit in just over a week. This is WASP 132b, a hot Jupiter that's teaching us incredible things about how gas giants behave when they're roasted by stellar radiation. And trust me, by the end of this video, you'll understand why astronomers are so excited about this distant world. But before we dive into WASP 132b specifically, let's quickly talk about exoplanets in general, because understanding what makes this planet special requires knowing what we're comparing it to. Section 1. The discovery of WASP 132b. WASP 132b was discovered by the Wide-Angle Search for Planets project, usually just called WASP. This is a collaboration between multiple institutions using robotic telescopes to monitor millions of stars searching for planets. WASP consists of two facilities, Super WASP North in the Canary Islands and Super WASP South in South Africa. Together, these arrays of wide-field cameras can monitor huge swaths of the sky simultaneously, watching hundreds of thousands of stars every night. WASP 132b was discovered using the transit method. Here's how it works. Imagine you're watching a streetlight, and every few minutes, a bug flies in front of it. Each time the bug passes, the light dims very slightly. If you graph the brightness over time, you'd see regular dips. That's basically what astronomers do with stars. When a planet passes in front of its star, what we call a transit, it blocks a tiny fraction of the star's light. For a Jupiter-sized planet, this might be a 1% dip in brightness. For an Earth-sized planet, it's more like 0.01%. Detecting these tiny variations requires precise measurements over weeks or months. Between 2006 and 2016, WASP South accumulated thousands of observations of a star cataloged as 1 SWASP J23215-435-410.8, later named WASP 132. The automated analysis pipeline detected periodic transit signals every 7.13 days with a depth of about 0.8%, indicating a large planet, roughly Jupiter-sized or bigger, in a close orbit. But detecting a transit signal isn't enough to confirm a planet. It could be an eclipsing binary star system or a background star creating a false positive. So astronomers conducted follow-up observations using multiple techniques. High-resolution imaging to make sure there weren't any companion stars creating confusion. Spectroscopic analysis to characterize the host star's properties, its mass, temperature, composition. Radial velocity measurements to detect the star's wobble caused by the planet's gravity and measure the planet's mass. By 2016, all the evidence converged. WASP 132b was confirmed as a genuine hot Jupiter, a massive gas giant orbiting extremely close to its star. The discovery was officially announced, adding another world to the exoplanet catalog. Now let's talk about what makes this planet so interesting. Section 2. Characteristics of WASP 132b. Let's break down WASP 132b's key characteristics, starting with the basics. Size. WASP 132b has a radius of approximately 1.13 Jupiter radii, so it's about 13% larger than Jupiter. That might not sound like much, but remember Jupiter is already massive, 11 times Earth's diameter. This planet is inflated by stellar heating, expanded beyond what it would be in a cold orbit. Mass: about 0.41 Jupiter masses. Actually less massive than Jupiter, only 41% of its mass. This tells us something immediately. Lower mass but larger size means density, approximately 0.31 grams per cubic centimeter. WASP: 132b is less dense than Saturn, one of the puffiest planets we know. This low density tells us WASP 132b is severely inflated by the intense stellar radiation it receives. The planet's interior is hot, so hot that it can't contract efficiently under its own gravity. Instead, it remains bloated, its atmosphere extended far into space. Inside WASP 132b, we probably have a small rocky/icy core at the center, perhaps 5 to 15 Earth masses. An inner envelope of metallic hydrogen, where extreme pressure forces hydrogen atoms to shed electrons and behave like a metal. An outer envelope of molecular hydrogen transitioning to atomic hydrogen. A hot atmosphere of hydrogen and helium with trace molecules. How does WASP 132b compare to other hot Jupiters we've discovered? It's in the moderately inflated category, expanded significantly, but not as extreme as some planets like WASP 107b, which is incredibly puffy. Its low mass combined with moderate to high irradiation creates this inflated structure. What makes WASP 132b particularly interesting for study is that it represents a common type of hot Jupiter, not an extreme outlier, but a typical example of what happens when you place a sub-Jupiter mass planet very close to a star. Understanding these typical cases is just as important as studying the extremes. Section 3. Orbit and temperature. Now let's talk about WASP 132b's orbit, because this is where things get really interesting. WASP 132b orbits at approximately 0.077 AU from its host star. To put that in perspective, Mercury orbits at 0.39 AU from our Sun. WASP 132b is 5 times closer to its star than Mercury is to ours. Orbital period: 7.1344 days. Just over a week to complete one orbit. A year on WASP 132b lasts only 171 hours. At this proximity, WASP 132b is almost certainly tidally locked, meaning the same side always faces the star, just like our moon always shows the same face to Earth. This creates a permanent day side and a permanent night side. Let's talk temperature. WASP 132b's equilibrium temperature. The temperature it would have if heat were distributed evenly across its surface is approximately 1,400 to 1,500 Kelvin. That's about 1,100 to 1,200 degrees Celsius, or 2,000 to 2,200 degrees Fahrenheit. To give you perspective, water boils at 373 K. Lead melts at 600 K. Most rocks melt around 1,500 to 1,800 K. WASP 132b's atmosphere, 1,400 to 1,500 K. The models predict powerful equatorial jet streams racing eastward at 4 to 6 kilometers per second, transporting heat from the blistering day side toward the cooler night side. The temperature difference drives this circulation. Hot air rises on the day side, flows to the night side aloft, cools and sinks, then returns at lower altitudes. Section 4. Atmospheric Studies. Okay, so we know WASP 132b is hot, massive, and inflated. But what's actually in its atmosphere? This is where things get really exciting, because astronomers have been able to study WASP 132b's atmosphere in detail using a technique called transmission spectroscopy. Here's how transmission spectroscopy works when WASP 132b transits in front of its star, some starlight passes through the planet's atmosphere before reaching us. Different molecules in the atmosphere absorb light at different wavelengths. By comparing the star spectrum during transit to its spectrum when the planet isn't transiting, we can detect which molecules are absorbing light, revealing the atmosphere's composition. Observations of WASP 132b have revealed several atmospheric components. Sodium, Na, strong absorption features in the optical spectrum. Sodium exists as atomic vapor at these temperatures. Individual sodium atoms floating in the atmosphere absorbing yellow-orange light. Hydrogen and helium, the dominant atmospheric constituents, probably 98 to 99% of the atmosphere by number. These are the lightest elements and were captured from the Planetary nebula when the planet formed. Possible water vapor, H2O. Some observations suggest water vapor features in the near-infrared, though confirming this requires careful analysis to separate planetary signals from stellar and instrumental effects. The detection of sodium is particularly important. Sodium absorption is one of the easiest atmospheric features to detect from ground-based telescopes because it produces strong, distinctive absorption lines. The fact that we see sodium tells us the atmosphere isn't completely clouded. There are clear or partially clear regions where we can probe atmospheric composition. Some observations suggest high-altitude hazes or clouds might exist at certain atmospheric levels, potentially made of silicates, metal compounds, or photochemical products. The exact cloud composition and distribution remains an area of active research. The atmospheric structure probably looks something like this. Upper atmosphere, low pressure hot, tenuous gas with atomic hydrogen, sodium vapor, and other atoms. Temperature around 1,400 to 1,600 K. Mid-atmosphere, pressure increases, temperature varies with altitude. This is where we're probing during transits. Mix of atoms and some molecules. Deep atmosphere, high-pressure molecular hydrogen dominates. Temperature rises to thousands of Kelvin, eventually transitions to metallic hydrogen deeper down. What makes WASP 132b's atmosphere particularly interesting is that it appears relatively clear compared to some hot Jupiters, which are so cloudy we can't detect any molecular features. This clarity makes it an excellent target for detailed atmospheric studies. We can actually see what's going on rather than just looking at a featureless haze. Section 5. Why WASP 132b matters. So why should we care about WASP 132b? It's not habitable, it's hundreds of light years away, and it's not even the most extreme hot Jupiter we've found. What makes it scientifically valuable? Host. Several reasons make WASP 132b important for exoplanet science. First, understanding planetary inflation. WASP 132b's low density, 0.31 g/cm superscript 3, results from stellar heating inflating the planet. But exactly how does this work? How does energy from the star get transported deep enough into the planet to prevent contraction? Theories include ohmic dissipation, atmospheric winds interacting with magnetic fields generating heat, breaking gravity, waves depositing kinetic energy, direct radiative heating in the deep atmosphere. WASP 132b, as a moderately inflated example, helps test these theories. Its properties constrain which heating mechanisms must be operating and with what efficiency. Second, atmospheric chemistry. WASP 132b's atmosphere is hot enough that chemistry operates in extreme regimes we can't replicate in laboratories. Molecules dissociate, atoms exist as vapors, chemical reactions proceed at rates millions of times faster than on Earth. By studying this alien chemistry, we learn how molecules behave at extreme temperatures, what compounds can form in hot atmospheres, how atmospheric circulation affects chemistry, transporting species from hot to cool regions where they recondense. Third, migration history. Hot Jupiters like WASP 132b can't form where we find them. There's not enough material so close to stars to build gas giants. They must form farther out beyond the snow line, where water ice exists, and then migrate inward. But how? Two main theories. Disk migration. The young planet interacts gravitationally with the protoplanetary disk, slowly spiraling inward while the disk is still present. Dynamical scattering. Multiple planets form and gravitationally scatter each other, sending one planet onto an eccentric orbit that tidal forces later circularize close to the star. WASP 132b's nearly circular orbit and system architecture provide clues about which mechanism operated. Each hot Jupiter adds to the statistical sample, helping us understand which migration pathways are most common. Fourth, population statistics. WASP 132b isn't unusual, and that's the point. It represents a common type of hot Jupiter. By studying many planets like WASP 132b, we build up population statistics. How common are inflated hot Jupiters? How does inflation correlate with stellar irradiation, planet mass, stellar metallicity? These statistics constrain formation and evolution models. They tell us how planetary systems assemble themselves and what determines which systems produce hot Jupiters versus maintaining planets on wider orbits like our solar system. Think of it this way. If we only studied Earth, we'd have a very limited understanding of planets. We need the Jupiters, the Mars, the Venus. Similarly, to understand gas giants, we need to study many examples, the extreme ones and the typical ones. WASP 132b is a valuable, typical example that helps define the norm against which we compare the extremes. Section 6. Future observations. The study of WASP 132b is far from over. In fact, the most exciting observations may still be ahead of us. Let's talk about what's next. The James Webb Space Telescope, launched in December 2021 and now fully operational, represents a revolution in exoplanet atmospheric studies. JWST's capabilities for studying WASP 132b include extended wavelength coverage. JWST observes from 0.6 to 28 microns, far into the infrared, where hot planets like WASP 132b emit most of their light. This allows detailed atmospheric composition measurements, detection of molecules that are invisible at optical wavelengths, precise temperature mapping, higher sensitivity. JWST's 6.5-meter mirror collects far more light than previous space telescopes, enabling detection of trace atmospheric species, measurements of atmospheric winds through Doppler shifts, detailed phase curves tracking brightness throughout the orbit. Specifically for WASP 132b, JWST could confirm water vapor detection and measure its abundance precisely, testing whether hot Jupiters have solar composition atmospheres or are enriched in heavy elements. Detect carbon-bearing molecules like carbon monoxide, CO, carbon dioxide, CO2, or methane, CH4, revealing the carbon-to-oxygen ratio, which constrains where and how the planet formed. Map the day-night temperature distribution through phase curve observations, measuring how efficiently atmospheric circulation redistributes heat. Search for clouds and hazes, determining their composition, altitude, and coverage across the planet. Visual, ground-based ELT concepts. Beyond JWST, the next generation of ground-based telescopes will revolutionize exoplanet science. With these facilities and extra-large telescopes in the near future, astronomers could directly measure wind speeds through Doppler shifts of molecular lines, detect atmospheric circulation patterns in unprecedented detail, search for atmospheric variability, weather changes, clouds forming and dissipating. Looking even further ahead, proposed missions like the Habitable Worlds Observatory in the 2040s might even directly image gas giants like WASP 132b, separating the planet's light from its star and studying it directly rather than just during transits. Each technological advancement provides new tools for understanding these alien worlds. WASP 132b, discovered by relatively modest ground-based telescopes, will continue yielding scientific insights as our observational capabilities improve. Section 7. Conclusion. WASP 132b reminds us that the universe is filled with worlds vastly different from Earth. Planets that challenge our understanding, that operate under physical conditions we can barely imagine, that expand our knowledge of what's possible in planetary science. Every planet we discover, every atmosphere we study, every data point we collect adds to our understanding of how planetary systems work, including our own. The techniques we develop to study hot Jupiters like WASP 132b will eventually be applied to smaller, cooler planets in habitable zones, bringing us closer to answering whether life exists elsewhere. 1,200 light-years away, WASP 132b continues its relentless orbit. Every 7 days, another year passes on this scorching world. The same hemisphere forever faces the star, heated to temperatures that would melt rock. Supersonic winds race through its atmosphere. Sodium atoms absorb starlight, and telescopes across Earth and in space watch, measure, and learn. Next, let's take a deep dive into TRAPPIST 1e, Earth's possible twin in a 7-planet system. 40 light-years from Earth, 7 worlds orbit a tiny red dwarf star. 3 of them sit in the habitable zone, the region where liquid water could exist. One of these planets, TRAPPIST 1e, might be the most Earth-like world we've ever discovered. Similar size, similar density, right temperature for liquid water, possibly even an atmosphere. This is the story of the planet that could change everything we know about life in the universe. Hey everyone, welcome back to the channel. Today, we're diving deep into one of the most exciting discoveries in astronomy, TRAPPIST 1e, a planet that might just be humanity's best candidate for finding life beyond Earth. For thousands of years, humans have looked up at the stars and asked, are we alone? Is Earth the only planet with life? For most of history, we couldn't even prove other planets existed beyond our solar system. But in the past 30 years, everything has changed. We've discovered over 5,600 confirmed exoplanets, worlds orbiting distant stars. Some are gas giants larger than Jupiter. Some are rocky super-Earths. Some orbit so close to their stars they're literally evaporating. And some, just maybe, could harbor life. But here's the challenge. Most exoplanets we've found are either too hot, too cold, too large, or orbiting stars too different from our Sun to realistically support life as we know it. Finding planets that are actually Earth-like, rocky, temperate, with potential for liquid water is incredibly rare. That's what makes the TRAPPIST-1 system absolutely extraordinary. Not only does it have 7 Earth-sized planets, which is remarkable enough, but 3 of them orbit in the habitable zone. And one of those 3, TRAPPIST-1e, might be the most promising candidate for extraterrestrial life we've ever found. Today, we're going to explore everything about TRAPPIST-1e, how it was discovered, what makes it so Earth-like, whether it could actually harbor life, and what future observations might reveal. By the end of this video, you'll understand why astronomers are so excited about this tiny world orbiting a star you can't even see with your naked eye. Let's get started. Section 1. The TRAPPIST-1 system. Before we dive into TRAPPIST-1e specifically, we need to understand the incredible system it's part of. TRAPPIST-1 is what astronomers call an ultra-cool red dwarf. Basically one of the smallest, coolest, and dimmest stars that can still fuse hydrogen in its core. It's only about 9% the mass of our Sun and roughly the size of Jupiter. If you could place TRAPPIST-1 next to our Sun, it would look like a marble next to a beach ball. This tiny star is located about 40 light-years away in the constellation Aquarius. Now, 40 light-years might sound like a huge distance, and it is about 235 trillion miles, but in cosmic terms, this is practically our backyard. There are only a few hundred stars closer to Earth than TRAPPIST-1. But here's what makes TRAPPIST-1 truly special. It hosts 7 Earth-sized planets, all orbiting closer to their star than Mercury orbits our Sun. This is the most planets ever discovered in a single system around a red dwarf, and all 7 are roughly Earth-sized, between 0.76 and 1.13 times Earth's radius. So we have 3 planets, D, E, and F, sitting right where temperatures could allow liquid water. But TRAPPIST-1e is considered the sweet spot. It receives almost exactly the same amount of stellar energy that Earth receives from the Sun. Its size and mass are incredibly Earth-like, and it's positioned perfectly for temperate conditions. This system is so compact that if you were standing on one of these planets, you'd see the other planets in the sky larger than the Moon appears from Earth. Imagine looking up and seeing another Earth-sized world hanging in your sky, perhaps with continents and oceans visible. That's what the TRAPPIST-1 system might be like. But how did we discover this incredible system? That's what we're exploring next. Section 2, the discovery. The story of TRAPPIST-1's discovery begins with a small telescope in the Atacama Desert of Chile. In 2010, astronomers built TRAPPIST, which stands for Transiting Planets and Planetesimals Small Telescope. Despite the name, this wasn't a huge observatory. It's actually a relatively modest 60-centimeter telescope, about 2 feet across. But it was designed with one specific purpose: to search for planets around ultra-cool red dwarf stars. We focused on ultra-cool dwarfs because even though they're dim, their small size means that Earth-sized planets create relatively large transit signals. An Earth-sized planet transiting a star like our Sun would block 0.01% of its light, extremely difficult to detect. But the same planet transiting TRAPPIST-1 blocks about 1% of the light, 100 times easier to detect. In 2015, the TRAPPIST team began monitoring TRAPPIST-1, cataloged as 2-mass J2306-2928-05-02285. Over months of observations, they noticed something remarkable: periodic dips in the star's brightness, the telltale sign of planets transiting in front of the star. By May 2016, the team had detected 3 planets in the system. They announced the discovery in a paper published in the journal Nature, and the astronomy community went wild. 3 Earth-sized planets around one star was already remarkable. But then came the game changer. NASA's Spitzer Space Telescope, an infrared observatory in space, joined the search. Over 20 days in late 2016, Spitzer observed TRAPPIST-1 continuously, and what it found was unprecedented. The data revealed not 3, but 7 planets. The discovery was announced in February 2017 at a major NASA press conference, making headlines worldwide. This was the first known system with 7 roughly Earth-sized planets, and 3 of them were in the habitable zone. And TRAPPIST-1e was immediately recognized as special. Its position, size, and estimated temperature made it the most Earth-like of the 7 worlds. Let me quickly explain how the transit method works, because it's crucial to understanding how we know what we know about TRAPPIST-1e. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light. By measuring exactly how much light is blocked, and for how long, we can calculate the planet's size from how much light is blocked, the orbital period from how often transits occur, the orbital distance from the period and stellar properties, the temperature from the distance and stellar luminosity. And by observing transits at different wavelengths and watching how the planets gravitationally tug on each other, We can also determine their masses and densities, telling us whether they're rocky like Earth or gaseous like Jupiter. For TRAPPIST-1e, these measurements revealed something incredible. Let's look at what makes this planet so special. Section 3. Characteristics of TRAPPIST-1e. TRAPPIST-1e is classified as a super-Earth, not because it's necessarily larger than Earth, but because it's in the size range that's larger than Earth but smaller than Neptune. But here's what's amazing. TRAPPIST-1e is actually almost exactly Earth size. This similar density is hugely significant. It tells us TRAPPIST-1e is almost certainly a rocky planet with an iron core and silicate mantle, just like Earth. It's not a mini Neptune with a thick hydrogen atmosphere. It's not a water world. It's a rocky planet that could potentially have Earth-like composition. Inside TRAPPIST-1e, we probably have an iron-nickel core, perhaps slightly smaller than Earth's proportionally, a rocky silicate mantle, possibly a thin crust, and potentially an atmosphere, though we haven't confirmed that yet. Now let's talk about its orbit, because this is where things get really interesting. TRAPPIST-1e orbits its star at a distance of only 0.028 AU. That's just 4.2 million kilometers, or about 2.6 million miles. For comparison, Mercury orbits the Sun at 0.39 AU. TRAPPIST-1e is about 14 times closer to its star than Mercury is to ours. Now, you might think, doesn't that mean it's insanely hot? And if TRAPPIST-1e orbited our Sun at that distance, yes, it would be instantly vaporized. But remember, TRAPPIST-1 is an ultra-cool red dwarf, only about 2,500 Kelvin at its surface, compared to the Sun's 5,778 K, and it's tiny and dim. Because of the star's coolness, even though TRAPPIST-1 east orbits very close, it receives almost exactly the same amount of energy per square meter that Earth receives from the Sun. The equilibrium temperature, the temperature the planet would have without an atmosphere, is estimated at about 246 Kelvin or minus 27 degrees Celsius. That's actually colder than Earth's equilibrium temperature of 255 K. But here's the key. Earth's surface is warmer, about 288 K or 15 degrees Celsius, because of our atmosphere's greenhouse effect. If TRAPPIST-1e has a similar atmosphere, it could have a surface temperature warm enough for liquid water. The orbital period is 6.1 days, so a year on TRAPPIST-1e lasts just 6 Earth days. And because of tidal locking, which is almost certain at this close distance, one side of the planet permanently faces the star while the other is in eternal darkness. This tidal locking has major implications. The day side would be constantly illuminated by the dim red sun, while the night side would never see starlight except from distant stars. However, if the planet has an atmosphere, winds would redistribute heat, potentially making large portions of the planet habitable despite the locking. So to summarize, TRAPPIST-1e is Earth-sized, rocky, orbits in the habitable zone at the right distance for liquid water temperatures, and receives Earth-like stellar flux. But the big question is, does it actually have the conditions for life? Section 4. Potential for habitability. Here's where things get both exciting and uncertain. TRAPPIST-1e has the right size, the right position, and the right temperature. But having the potential for habitability is very different from being actually habitable. For a planet to support life as we know it, you need several things. Rocky composition, we've got that, confirmed by density. Right temperature for liquid water, we've got that. It's in the habitable zone. An atmosphere? Unknown. This is the critical question. Water? Unknown. Stable conditions over long periods? Complicated. More on this shortly. Let's start with the atmosphere question, because it's probably the single most important factor. Having an atmosphere isn't guaranteed. Mars is in our Sun's habitable zone, and once had an atmosphere and liquid water, but lost most of it. Venus has a thick atmosphere, but runaway greenhouse effect made it hellish. Mercury has essentially no atmosphere. Whether TRAPPIST-1e has retained an atmosphere depends on many factors. Here's one of the biggest challenges. Red dwarf stars, especially young ones, are extremely active. They produce frequent, powerful stellar flares, sudden eruptions of radiation and energetic particles. These flares can strip away planetary atmospheres over time, especially for planets orbiting so close. TRAPPIST-1 is relatively old, about 7.6 billion years, so it's less active than young red dwarfs. But we don't know for certain whether TRAPPIST-1e managed to hold onto an atmosphere, or if it was stripped away early in the system's history. This is where recent observations come in. In 2023, astronomers used the James Webb Space Telescope to observe TRAPPIST-1b, the innermost, hottest planet, to search for an atmosphere. They found that TRAPPIST-1b probably doesn't have a significant atmosphere, likely because it's too close and too hot. But here's the crucial point. TRAPPIST-1e is farther out, receives less intense radiation, and is cooler. The conditions that stripped the atmosphere from Planet B might not apply to Planet E. We just don't know yet, but observations are planned. If TRAPPIST-1e does have an atmosphere, what might it be like? Possibility 1. Thin atmosphere like Mars. Mostly CO2, low pressure. Some liquid water possible in equatorial regions or underground. Limited habitability. Possibility 2. Earth-like atmosphere. Nitrogen-oxygen mixed with greenhouse gases. Moderate pressure. Liquid water oceans possible. High habitability potential. Possibility 3. Thick atmosphere like Venus. Heavy CO2, very high pressure. Runaway greenhouse effect. Surface too hot for liquid water despite distance. Uninhabitable. Possibility 4. No atmosphere. Stripped by stellar activity early on. Exposed to space radiation. No liquid water. Uninhabitable. Current models suggest that if TRAPPIST-1e has an atmosphere similar to Earth's, with nitrogen, oxygen, and some greenhouse gases, the surface temperature could be around 0 to 20 degrees Celsius, perfect for liquid water. Some models even suggest it could have a global ocean, though that's speculative. If TRAPPIST-1e is an ocean world, it might look quite different from Earth. With one side always facing the star, you might have a pattern where water evaporates on the day side, travels as vapor through the atmosphere, and freezes as ice on the night side, creating a dynamic water cycle. But here's something to keep in mind. Life on Earth thrives in incredibly diverse environments, from boiling hot springs to frozen Antarctic lakes to deep ocean trenches. If TRAPPIST-1e has liquid water anywhere, even in limited regions, it might be habitable, even if conditions are far from Earth-like overall. So the big question, does TRAPPIST-1e have life? Honest answer, we have absolutely no idea. We don't even know if it has an atmosphere yet, let alone liquid water, let alone life. But the exciting part is that we're actually going to be able to answer some of these questions in the near future. Section 5. Scientific importance and future research. Even if TRAPPIST-1e turns out to be uninhabitable, its discovery is monumentally important for science. Here's why TRAPPIST-1e matters so much. First, it's one of the best targets we have for atmospheric characterization. The planet is close enough, 40 light years, transits frequently, every 6 days, orbits a dim star, making atmospheric signals easier to detect, and has properties suggesting it could be rocky with an atmosphere. There are very few planets that check all these boxes. TRAPPIST-1e is literally one of the top targets for the James Webb Space Telescope and future observatories searching for signs of life. If we're going to detect biosignatures, chemical signs of life, on an exoplanet anytime in the next couple decades, TRAPPIST-1e is one of our best shots. Second, It helps us understand the prevalence of habitable worlds. Red dwarfs make up about 70% of all stars in our galaxy. If red dwarf planets can be habitable, despite stellar activity and tidal locking challenges, then potentially habitable worlds are far more common than if only sun-like stars can host life. TRAPPIST-1e is a test case. If this planet is habitable, it suggests billions of similar worlds could exist throughout the Milky Way. Third, it teaches us about planetary system formation. Having 7 planets, all similar in size, but with potentially very different compositions and atmospheres, is a natural laboratory for studying how planets form and evolve. Why do some retain atmospheres while others lose them? How do planets at different distances in the same system develop different characteristics? TRAPPIST-1e, along with its 6 siblings, helps answer these fundamental questions about planetary science. So what's next? We're scientists planning to learn about TRAPPIST-1e. James Webb Space Telescope is already observing the TRAPPIST-1 system. Over the next few years, JWST will conduct extensive observations of TRAPPIST-1e, specifically searching for atmospheric detection. Does it have an atmosphere at all? Composition. If yes, what's in it? CO2? Water vapor? Oxygen? Temperature mapping? How hot is the day side versus night side? Cloud coverage. Are there clouds? What kind? If JWST detects certain combinations of gases, like oxygen and methane together, or phosphine, or other chemicals that are produced by life and wouldn't naturally coexist without biological processes, that would be incredibly strong evidence for life. Now, we need to be careful here. Detecting these gases wouldn't be proof of life. There might be geological or chemical processes we don't understand that could produce them, but it would be compelling enough that follow-up observations would become a top priority. The JWST observations of TRAPPIST-1e are scheduled for 2024 to 2026, with results expected in the next few years. This is happening right now. We're living through the era when we might actually discover evidence of life on another world. Beyond JWST, even more powerful telescopes are coming. Extremely large telescopes in 10 or more years. Ground-based 30 to 40-meter telescopes with adaptive optics. LUVOIR/Habitable Worlds Observatory in 20 or more years. Space telescope designed specifically to image and characterize Earth-like planets. These future missions might actually be able to directly image TRAPPIST-1e, separating its light from the star and taking actual pictures, resolving continents and oceans if they exist. We're talking about photographing another Earth. Think about that for a second. In our lifetimes, we might look at images of oceans, clouds, maybe even green vegetation on a planet 40 light-years away. That's incredible. All right, let's wrap up by reviewing what we've learned about TRAPPIST-1e. TRAPPIST-1e represents our best near-term opportunity to answer one of humanity's oldest questions. Are we alone? Whether TRAPPIST-1e has life or not, its discovery has already expanded our understanding of what's possible. A decade ago, we didn't know systems like TRAPPIST-1 existed. Now we know they're out there. 7 Earth-sized worlds, 3 potentially habitable, orbiting a single tiny star. If this can happen around one star, it can happen around billions. The galaxy might be filled with worlds like TRAPPIST-1e, each with its own oceans, its own weather, perhaps its own life. Some questions to think about. If we detect oxygen in TRAPPIST-1e's atmosphere, what would that mean? Could life evolve on a tidally locked planet? What would it be like to live on a world with 6 other Earth-sized planets visible in the sky? 40 light-years away, TRAPPIST-1e continues its eternal orbit. 6 days to complete a year. One side bathed in dim red starlight, the other in perpetual darkness. Does it have oceans? Clouds? Life? We don't know yet. But soon, maybe in just a few years, we might have answers. Earth is alright, but what if it could get even better? With this next world, it just me. GHT K2-134b. A super-Earth revealing secrets of planetary diversity. 400 light-years from Earth, a planet orbits a sun-like star. It's 1.4 times Earth size, completes an orbit every 10 days, and sits far too close to its star for life, as we know it. But K2-134b isn't important because it might harbor life. It's important because of what it teaches us about how planets form, evolve, and populate our galaxy. This is the story of a super-Earth discovered by a mission that refused to quit, and what this distant world reveals about the incredible diversity of planets filling our universe. Today we're exploring K2-134b, a super-Earth discovered by NASA's K2 mission that's helping scientists understand the incredible variety of planetary systems in our galaxy. Here's a fascinating question. Why are planets so different? Our solar system has small rocky worlds close to the sun and giant gas planets farther out. But is that arrangement universal? Or does nature create planetary systems in wildly different configurations? Over the past 3 decades, we've discovered that planetary systems come in incredible variety. Hot Jupiters orbiting closer than Mercury. Super-Earths that don't exist in our solar system. Mini Neptunes that blur the line between rocky and gaseous worlds. Each discovery expands our understanding of what's possible. K2-134b, discovered in 2017, is one of thousands of planets found by NASA's missions that's helping us understand this diversity. It's classified as a super-Earth, a planet larger than Earth but smaller than Neptune. And its properties tell us important things about how planets form and what determines whether they end up rocky or gaseous. So today we're going to explore how K2-134b was discovered by the K2 mission. What makes this planet scientifically interesting? What it teaches us about planetary formation, and why studying planets like this matters for understanding our place in the universe. Let's dive in. Section 1. The K2 mission. To understand K2-134b's discovery, we need to talk about one of the most successful planet-hunting missions ever, the Kepler Space Telescope and its second life as the K2 mission. NASA's Kepler Space Telescope launched in March 2009 with one primary goal: stare at a single patch of sky containing about 150,000 stars and search for planets using the transit method. Over 4 years, Kepler discovered over 2,300 confirmed exoplanets and revolutionized our understanding of how common planets are. Kepler was incredibly successful. So successful that it transformed exoplanet science from discovering individual planets to studying planetary populations and statistics. We learned that planets are common, that most stars have planets, and that planetary systems come in configurations we never predicted. But in May 2013, disaster struck. Kepler relied on 4 reaction wheels, spinning devices that kept the telescope precisely pointed at its target stars. When the second wheel failed, Kepler could no longer maintain the precise pointing needed for its original mission. The mission seemed over. Years of planning, billions of dollars, and the most productive planet-hunting telescope ever built, seemingly rendered useless by mechanical failure. But the Kepler team refused to give up. They devised an ingenious solution: use pressure from sunlight, solar radiation pressure, as a virtual reaction wheel. By carefully balancing the spacecraft and pointing it along the ecliptic plane, they could maintain enough stability to continue observations. This was the birth of the K2 mission, Kepler's second light. Instead of staring at one field forever, K2 would observe different fields along the ecliptic for about 80 days each, called campaigns. Between 2014 and 2018, K2 observed 19 campaigns, monitoring over 500,000 stars and discovering hundreds of new planets. K2-134b was discovered during one of these campaigns. a testament to engineering ingenuity turning potential failure into continued success. K2 was remarkable because it gave us a second chance to find planets, but with a different strategy. Instead of one deep stare, we got many shorter looks at diverse stellar populations. K2 discovered planets around young stars, old stars, different types of stars, expanding the diversity of exoplanets we could study. Section 2. The Discovery. During one of K2's campaigns, the telescope observed a star cataloged as EPIC 246471491, later designated K2-134. Over the 80-day observation period, K2's sensitive detectors recorded a periodic dimming in the star's brightness. This is the transit method in action, and it's worth explaining because it's how we've discovered most known exoplanets. Imagine you're watching a streetlight at night, and every few minutes, a bug flies in front of it. Each time the bug passes, the light dims slightly. The transit method works exactly the same way. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the starlight, creating a characteristic dip in brightness. From this transit signal, astronomers can measure several crucial properties. The planet's size, how much light is blocked, tells us how large the planet is relative to its star. The orbital period, how often transits occur, tells us how long the planet takes to orbit. The orbital distance, using Kepler's laws, we can calculate how far the planet is from its star. The temperature, from distance and stellar properties, we can estimate temperature. For K2-134, the transit signal showed periodic dimming every 10.2 days. Transit depth of about 0.15%, indicating a planet roughly 1.4 times Earth's radius. Transit duration consistent with a close orbit around a sun-like star. But detecting a transit signal is only the first step. Could it be something other than a planet? Could it be an eclipsing binary star system? A background star creating confusion? Instrumental noise? Confirming K2-134b as a genuine planet required follow-up observations from ground-based telescopes. High-resolution imaging verified that K2-134 is a single star with no close stellar companions that could create false signals. Spectroscopic observations measured the star's properties, its temperature, mass, composition, and age. And radial velocity measurements attempted to detect the gravitational wobble induced by the planet's mass. Radial velocity observations for K2-134b didn't definitively measure its mass. The signal was too small given the precision of available instruments. But they could place upper limits. The planet had to be smaller than a certain mass to be consistent with observations. The discovery was announced in 2017 as part of a catalog of K2 planets. K2-134b joined hundreds of other worlds discovered by the mission, each adding to our understanding of planetary diversity. Section 3. Characteristics of K2-134b. So what exactly is K2-134b? Let's break down its characteristics. Size and classification. K2-134b has a radius of approximately 1.43 Earth radii, so it's about 43% larger than Earth. This places it firmly in the super-Earth category, which typically refers to planets between 1.25 and 2 Earth radii. Now, super-Earth can be a bit misleading. It doesn't necessarily mean the planet is like Earth, just bigger. Super-Earths can be rocky like Earth, gaseous like Neptune, or something in between. The classification is really just about size. Mass. Without a precise radial velocity measurement, we don't have an exact mass for K2-134b. However, based on its size and statistical relationships between size and mass for exoplanets, astronomers estimate it's probably between 2 and 6 Earth masses. This estimate uses empirical relationships between planetary radius and mass derived from planets where both have been measured. For planets around 1.4 Earth radii, masses typically range from 2 to 6 Earth masses, depending on composition. Rocky planets are denser and more massive for their size, while planets with thick atmospheres are less dense. So K2-134b could be a rocky super-Earth with a thin atmosphere, a rocky core with a thick hydrogen-helium envelope, a water-rich world, or some combination. Without knowing the mass precisely, we can't definitively say which it is. Orbital characteristics. K2-134b orbits its star every 10.21 days. So a year on K2-134b is just 10 Earth days. The orbital distance is approximately 0.098 AU, about 14.6 million kilometers or 9 million miles. For perspective, Mercury orbits the Sun at 0.39 AU. K2-134b orbits about 4 times closer to its star than Mercury does to ours. This close orbit means K2-134b is almost certainly tidally locked, with one hemisphere always facing the star and the other in perpetual darkness. Temperature. Given its proximity to the star, K2-134b is hot. The equilibrium temperature, assuming no atmosphere or efficient heat redistribution, is estimated at around 650 to 750 Kelvin, or about 380 to 480 degrees Celsius, 720 to 900 degrees Fahrenheit. That's hot enough that water would be steam, not liquid. Lead would be soft or molten. The surface would glow red from thermal emission. Any atmosphere would be extremely dynamic. The host star, K2-134, is a G-type star similar to our Sun. It has about 0.97 solar masses, 97% the Sun's mass, slightly cooler temperature, and is probably several billion years old, comparable to our Sun's age. The similarity between K2-134 and our Sun makes this system interesting for comparative studies. Why does K2-134 host a close-in super-Earth while our Sun doesn't? What determines whether planetary systems end up looking like ours or like K2-134? Section 4. Is it habitable? Okay, let's address the big question. Could K2-134b be habitable? Could it host life? Short answer, almost certainly not. At 650 to 750 K, K2-134b is way too hot for liquid water, a key requirement for life as we know it. Any water would exist as steam. The planet orbits well inside the habitable zone, the region where temperatures could allow liquid water. The habitable zone around K2-134 is roughly 0.9 to 1.7 AU. K2-134b at 0.098 AU is about 9 to 17 times closer than it would need to be for habitability. It's not even close. But here's the thing. K2-134b's lack of habitability doesn't make it unimportant. In fact, studying planets like this teaches us crucial lessons about planetary formation and evolution that ultimately help us understand which planets can be habitable. Super-Earths like K2-134b are incredibly common in our galaxy, more common than Earth-sized planets or Jupiter-sized planets. But our solar system doesn't have any super-Earths. Why? What determines whether a planetary system produces super-Earths or not? By studying planets like K2-134b, their compositions, atmospheres, orbital arrangements, we learn about the processes that build planets and determine what types form where. This knowledge eventually helps us identify which planetary systems might host habitable worlds. So while K2-134b itself isn't habitable, understanding it is part of the larger puzzle of finding planets that are. Section 5. Scientific significance. Let's talk about why K2-134b matters for science. K2-134b contributes to several key areas of exoplanet research. 1. Understanding the radius valley. There's a fascinating feature in exoplanet populations called the radius valley, or Fulton gap. When you plot all discovered planets by size, there's a noticeable gap around 1.5 to 2 Earth radii. Fewer planets exist in this size range than you'd expect. Below the valley, roughly 1 to 1.5 Earth radii, are rocky super-Earths. Above the valley, 2 to 4 Earth radii, are mini-Neptunes with thick hydrogen-helium atmospheres. The valley represents the transition zone. K2-134b, at 1.43 Earth radii, sits right at the upper edge of the rocky super-Earth population, just below where the valley begins. Is it rocky? Does it have a thin atmosphere? A thick one? The radius valley is thought to be carved out by photoevaporation, stellar radiation stripping away atmospheres from planets that aren't massive enough to hold onto them. Planets above a certain mass threshold keep their atmospheres and remain mini-Neptunes. Planets below the threshold lose their atmospheres and shrink to rocky cores. K2-134b helps test this theory. Its size and position tell us about the boundary between rocky and gaseous planets, about how much atmosphere a planet this size can retain at this distance from a sun-like star. 2. Planetary formation models. How do super-Earths form? Do they form where we find them, or do they migrate from farther out? K2-134b's orbital distance, close but not extremely close, places it in an interesting regime for testing formation theories. Some models suggest super-Earths form beyond the snow line, the distance where water ice can exist, and then migrate inward. Others suggest they form in situ from the protoplanetary disk. K2-134b's properties constrain which scenario is more likely. 3. Stellar planet interactions. At 0.098 AU, K2-134b is close enough to its star that interactions between the star and planet become significant. Stellar wind, magnetic fields, tidal forces, all these affect the planet's evolution. If K2-134b has an atmosphere, it's probably losing material to space through atmospheric escape driven by stellar radiation. The rate of this loss depends on the planet's mass, the star's activity, and the atmosphere's composition. Studying these processes teaches us about how close-in planets evolve over billions of years. 4. Population statistics. Individual planets are interesting, but population statistics are powerful. By studying many planets like K2-134b, super-Earths around sun-like stars at various distances, we build statistical understanding of how common different types of planets are, where they form, how they're distributed. K2-134b is one data point in a data set of thousands, and together, these data points reveal the bigger picture of how planetary systems are organized throughout our galaxy. Section 6. Future Research. So what's next for K2-134b? What can future observations tell us? K2-134b faces some challenges as an observational target. Its host star is relatively faint, magnitude 12.4, which makes detailed observations difficult. And without a precise mass measurement, we can't fully characterize the planet. Better mass measurements. Future radial velocity observations with next-generation spectrographs could potentially measure K2-134b's mass more precisely. Instruments like ESPRESSO, HARPS-N, or future extremely large telescope spectrographs might achieve the precision needed. Knowing the mass would tell us the density, which reveals composition. A density of 8 to 10 G/cm superscript 3 would indicate a rocky, iron-rich planet. A density of 3 to 5 G/cm superscript 3 would suggest a rocky core with a substantial water or hydrogen-helium envelope. This one measurement would transform our understanding of K2-134b. Atmospheric studies. The James Webb Space Telescope could, in principle, attempt atmospheric characterization of K2-134b through transmission spectroscopy. However, the faintness of the host star makes this challenging. It would require many transits and long integration times. If attempted, JWST could search for water vapor, carbon dioxide, methane, other molecules that reveal atmospheric composition. Extremely large telescopes in 20 or more years. The next generation of ground-based telescopes, the Extremely Large Telescope, the Giant Magellan Telescope, the 30-meter telescope, will have unprecedented light-gathering power and precision. These facilities might be able to measure K2-134b's mass through ultra-precise radial velocity, characterize its atmosphere at high spectral resolution, detect chemical signatures that reveal composition and evolution. Long-term monitoring. One underappreciated aspect of exoplanet science is the value of long-term monitoring. Observing K2-134b repeatedly over years or decades could reveal transit timing variations indicating additional planets, atmospheric variability or weather patterns, orbital evolution or tidal effects, changes in stellar activity affecting the planet. Even if K2-134b itself isn't extensively studied, it contributes to comparative studies. By analyzing many super-Earths across different systems, astronomers identify patterns and test theories about planetary formation, composition, and evolution. All right, let's wrap up by reviewing what we've learned about K2-134b. K2-134b isn't the most extreme planet. It's not the hottest, the largest, the closest, or the most Earth-like. But that's exactly what makes it valuable. Science advances not just through discovering extremes, but through characterizing the typical, the common, the representative examples. K2-134b is one of countless super-Earths orbiting sun-like stars throughout our galaxy. By understanding this planet, we understand a whole class of worlds that simply don't exist in our solar system. Every planet we discover, every measurement we make, every observation we conduct adds to our collective understanding of how planets form, how they evolve, what types exist, and where we should look for life. K2-134b was discovered by a mission that refused to quit. Engineers who turned mechanical failure into 4 more years of discoveries. It's fitting that this planet, discovered through ingenuity and perseverance, teaches us about diversity and resilience in planetary systems. 400 light-years away, K2-134b continues its rapid orbit. Every 10 days, another year passes on this hot super-Earth. We may never visit this world. We may never know for certain its exact composition or atmospheric chemistry. But through patient observation and scientific analysis, we learn from this distant world about the processes that shape all planets, including our own. If you like habitable worlds, you're going to love this next one. HD 3167c. The super-Earth perfect for atmospheric studies. 154 light-years from Earth, 3 planets orbit a bright star. One of them, HD 3167c, is a super-Earth perfectly positioned for one of the most important observations in astronomy, characterizing the atmosphere of a potentially rocky world outside our solar system. This planet is special. It's one of the brightest super-Earths ever discovered. It transits frequently, and its properties make it one of the absolute best targets for the James Webb Space Telescope and future observatories searching for signs of life beyond Earth. This is HD 3167c, a world that could help answer the question, what are the atmospheres of rocky planets really like? we're exploring one of the most scientifically valuable exoplanets ever discovered, HD 3167c, a super-Earth that astronomers are absolutely racing to study because it might give us our first clear look at the atmosphere of a rocky planet beyond our solar system. The search for life beyond Earth isn't just about finding planets in habitable zones. It's about understanding what these planets are actually like, their compositions, their atmospheres, whether they have the conditions that could support life. We've discovered thousands of exoplanets, but actually characterizing them, measuring what's in their atmospheres, determining their compositions, understanding their climates, is incredibly difficult. Most exoplanets are too faint, too far away, or orbit stars too dim for detailed atmospheric studies. That's what makes HD 3167c so special. This planet has almost everything you'd want in an atmospheric characterization target. It's relatively nearby at 154 light-years. It orbits a bright star, magnitude 8.9, visible with binoculars. It transits every 30 days, giving us frequent observation opportunities. And at 2.7 Earth radii, it's in the fascinating size range where planets could be rocky super-Earths or mini-Neptunes with thick atmospheres. But HD 3167c doesn't orbit alone. It's part of a three-planet system discovered between 2016 and 2017 by NASA's K2 mission and confirmed through multiple follow-up observations. Each planet tells part of the story of how this system formed and evolved. Today, we're going to explore how HD 3167c was discovered in this remarkable multi-planet system. What makes its characteristics so valuable for science? Why astronomers are so excited to study its atmosphere? What future observations might reveal? And how this one planet could transform our understanding of rocky worlds throughout the galaxy. Let's dive in. Section 1. The multi-planet system. Before diving into HD 3167c specifically, let's understand the system it's part of. HD 3167 is a K-type star, slightly cooler and smaller than our Sun, but still in the category of stable, long-lived stars. Here are its vital statistics. That magnitude of 8.9 is crucial. Most K2 and Kepler discoveries orbit stars with magnitudes of 11 to 16, much fainter. HD 3167's brightness makes it one of the best targets for follow-up observations, especially atmospheric characterization. HD 3167 hosts 3 known planets, discovered between 2016 and 2017. HD 3167b, innermost. Radius, 1.7 Earth radii. Mass, 5.0 Earth masses. Orbital period, 0.96 days, less than 1 Earth day. Distance, 0.0134 AU. Classification, super-Earth, probably rocky. Temperature, 500 K, way too hot. HD 3167c, middle, our focus today. Radius, 2.7 Earth radii. Mass, 9.8 Earth masses. Orbital period, 29.85 days, about 1 month. Distance, 0.1754 AU. Classification, super-Earth or mini-Neptune. Temperature, 500 K. Best atmospheric characterization target. HD 3167d, outermost. Radius, unknown, detected via radial velocity only. Minimum mass, 6.9 Earth masses. Orbital period, 8.5 days. Distance, 0.07 AU. Does not transit, orbital plane misaligned. This system is fascinating because it has 2 transiting inner planets, B and C, that we can study through transmission spectroscopy, and 1 non-transiting outer planet, D, detected only through radial velocity. The fact that planet D doesn't transit tells us the system isn't perfectly flat. The outer planet's orbit is tilted relative to the inner two. This orbital architecture, 2 transiting planets plus 1 non-transiting, provides clues about the system's dynamical history. Did gravitational interactions tilt planet D's orbit? Was there planet-planet scattering early in the system's history? These questions make HD 3167 not just interesting for individual planet studies, but for understanding how multi-planet systems evolve. Section 2. The Discovery. HD 3167's planets were discovered during K2's Campaign 8, which observed this region of sky from January to March 2016. K2 detected periodic dimming in HD 3167's brightness, the characteristic signature of transiting planets. 2 distinct transit signals appeared in the data. Shallow transits every 0.96 days. This was HD 3167b, the innermost planet. Deeper transits every 29.85 days. This was HD 3167c, our focus today. Let me remind you how the transit method works, because it's crucial to understanding what we know about HD 3167c. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light. The amount of light blocked depends on the planet's size relative to the star. For HD 3167c, which is 2.7 times Earth's radius orbiting a star 0.84 times the Sun's size, the transit blocks about 0.9% of the star's light, a signal clearly detectable with precise photometry. From the transit we measure planet size from depth of dimming, orbital period from how often transits occur, orbital distance from period using Kepler's laws, atmospheric signals from wavelength-dependent transit depth. But K2 could only tell us the planet size. To know its mass, and therefore its density and likely composition, we needed radial velocity follow-up. Between 2016 and 2017, multiple teams used high-precision spectrographs to measure HD 3167's radial velocity, how fast the star moves toward or away from us as planets gravitationally tug on it. These observations revealed not just 2 but 3 planets. The innermost, B, and middle, C, produced signals matching their known transit periods. But a third signal appeared at 8.5 days, a planet that didn't transit, indicating its orbit is tilted relative to the inner two. From radial velocity, astronomers measured HD 3167b, 5.0 plus or minus 0.7 Earth masses. HD 3167c, 9.8 plus or minus 1.0 Earth masses. HD 3167d, at least 6.9 Earth masses, minimum mass. Actual mass could be higher. Now here's where it gets really interesting. With both size and mass, we can calculate density, which tells us composition. That density of 2.0 g/cm superscript 3 for HD 3167c is precisely in the interesting range where we can't immediately tell composition. It could be a rocky planet with a substantial hydrogen-helium atmosphere, a water world with a thick steam atmosphere, a rocky core with a water/ice layer and thin atmosphere. The only way to know for sure is to study its atmosphere directly. And that's exactly what makes this planet so valuable. The system was announced in 2017, with multiple papers characterizing the planet's properties. Immediately, HD 3167c was identified as a prime target for atmospheric studies due to the bright host star and frequent transits. Section 3. Characteristics of HD 3167c. Let's dive deep into what makes HD 3167c so special. Size and mass. HD 3167c is a super-Earth, a planet larger than Earth but smaller than Neptune. Radius: 2.7 Earth radii, 170% larger than Earth. Mass: 9.8 Earth masses, nearly 10 times Earth's mass. Density: 2.0 g/cm superscript 3, intermediate between rock and water/gas. At 2.7 Earth radii, HD 3167c sits just above the radius valley. That gap in the exoplanet size distribution around 1.5 to 2.0 Earth radii that separates rocky super-Earth from mini-Neptunes with thick atmospheres. This position is scientifically fascinating because planets this size could have very different compositions. Scenario 1. Rocky with H/E atmosphere. Iron silicate core, 8 to 9 Earth masses. Hydrogen-helium envelope, 1 to 2 Earth masses, 5% by mass. Thick gaseous atmosphere, hundreds of km deep. Scenario 2. Water world. Rocky core, 6 to 7 Earth masses. Thick water/ice layer, 2 to 3 Earth masses. Steam atmosphere from heated water. Scenario 3. Hybrid. Rocky core with water layer. Thin hydrogen atmosphere. Complex layered structure. Host. The only way to distinguish these scenarios is through atmospheric observations, measuring what molecules are present, their abundances, and the atmospheric structure. That's why HD 3167c is so important. Orbital characteristics. HD 3167c orbits its star every 29.85 days, almost exactly 1 month. This is a relatively long period for exoplanets we can study in detail, which actually works in our favor. Distance: 0.1754 AU, about 26 million kilometers. Comparison: about 40% of Mercury's distance from the Sun. Orbital velocity: 45 km/s. Temperature: HD 3167c's equilibrium temperature is estimated at around 500 Kelvin, 227 degrees Celsius or 440 degrees Fahrenheit, assuming no atmosphere or heat redistribution. For perspective, Earth's equilibrium temperature, 255 K. Venus's surface temperature, 735 K. Mercury's average, 440 K. HD 3167c, 500 K. At 500 K, HD 3167c is too hot for liquid water on its surface. Water would be steam. However, this temperature is cool enough that complex molecules can exist in the atmosphere. Clouds might form, depending on composition. Atmospheric chemistry is rich and diverse. It's not so hot that molecules instantly dissociate. At 0.175 AU, HD 3167c is probably tidally locked. One hemisphere always faces the star, the other in perpetual darkness. However, if it has a substantial atmosphere, atmospheric circulation would redistribute heat, making large portions of the planet more temperate than the extremes of the day and night sides. Here's a technical but crucial point. Astronomers rate targets for atmospheric characterization using something called the transmission spectroscopy metric, TSM, basically a score measuring how good a planet is for atmospheric studies. HD 3167c has a TSM of about 44, which places it in the top tier of super-Earth/mini-Neptune targets for JWST observations. Section 4. Is it habitable? Okay, let's address the habitability question directly, because I know that's what a lot of you are wondering. Can HD 3167c support life? Almost certainly not. At 500 K surface temperature, HD 3167c is far too hot for liquid water. Water would exist only as steam. The planet orbits well inside the habitable zone, which for HD 3167 is roughly 0.5 to 1.0 AU. HD 3167c at 0.175 AU is about 3 times closer than the inner edge of the habitable zone. But here's the crucial point. HD 3167c's value isn't about habitability. It's about understanding planetary atmospheres. To eventually identify and confirm life on exoplanets, we need to develop techniques on easier targets, understand atmospheric chemistry under various conditions, learn to distinguish biological versus non-biological signatures, build experience interpreting complex spectra. HD 3167c is essentially a training ground for these techniques. It's bright enough and transits frequently enough that we can develop and refine our methods for atmospheric characterization. What we learn from HD 3167c will directly apply to studying potentially habitable worlds in the future. Think of it this way. HD 3167c is to atmospheric characterization what hot Jupiters were to exoplanet discovery. Not the ultimate targets, but the ones where we develop our skills and test our theories. Section 5. Atmospheric Studies. So what are scientists actually looking for in HD 3167c's atmosphere? Atmospheric characterization through transmission spectroscopy works by observing the planet's transit at many different wavelengths. Different molecules absorb light at different wavelengths, creating a spectral fingerprint. For HD 3167c, scientists are searching for water vapor, strong absorption at 1.4, 1.9, and 2.7 microns. If present, indicates volatile-rich composition. Keep biosignature in habitable planets, though not here. Hydrogen and helium, if abundant, indicates substantial primordial atmosphere. Suggests mini-Neptune classification. Would appear as Rayleigh scattering in UV/optical. Methane, absorption at 1.7, 2.3, 3.3 microns. In this temperature regime, could indicate carbon-rich atmosphere, or could form from chemical reactions. Carbon dioxide, strong absorption at 4.3 microns, could indicate secondary atmosphere from outgassing, or remnant of primordial atmosphere. Carbon monoxide, absorption at 2.3 and 4.6 microns, stable at high temperatures. Abundance ratio CO/CO2 reveals atmospheric chemistry. Clouds and hazes can mask molecular features, appear as muted or flat spectrum. Composition depends on temperature, silicates, salts, photochemical hazes. HD 3167c has already been observed multiple times. 2017 to 2018, ground-based observations. Preliminary atmospheric characterization attempts. Challenging due to faint signals from ground. 2019, Hubble Space Telescope. Multiple transits observed. Near-infrared spectroscopy. Results, tentative detection of water vapor, but significant atmospheric features. 2021 to 2023, additional ground-based campaigns. Building up observation statistics. Constraining atmospheric properties. The Hubble observations suggested HD 3167c might have a relatively clear atmosphere, not completely enshrouded in clouds. This is good news because cloudy atmospheres are much harder to characterize. Clear atmospheres show strong molecular features that reveal composition. But the real game changer is the James Webb Space Telescope. JWST's capabilities for HD 3167c include, with just a few transits observed by JWST, astronomers could definitively detect water vapor, if present, measure carbon-bearing molecules, determine atmospheric metallicity, constrain atmospheric structure, distinguish between rocky with atmosphere and water world scenarios. Different compositions would produce characteristic spectral signatures. If mini-Neptune with H/E, strong absorption features from H2O, CH4, Rayleigh scattering slope and optical, low atmospheric mean molecular weight. If water world, dominant H2O features, possibly high-pressure steam atmosphere indicators, high atmospheric mean molecular weight. If rocky with thin atmosphere, weak spectral features, possibly CO2 or other secondary atmosphere gases, very high mean molecular weight. This is why HD 3167c is so scientifically valuable. It's one of the few planets where JWST observations could definitively tell us what type of planet it is, answering fundamental questions about planetary composition and atmospheric retention. Section 6. Scientific significance. Let's zoom out and talk about why HD 3167c matters beyond just this one planet. HD 3167c contributes to several critical areas of planetary science. 1. Atmospheric retention and evolution. At 2.7 Earth radii and receiving moderate stellar flux, HD 3167c is in a regime where atmospheric retention is uncertain. Has it retained a primordial hydrogen-helium atmosphere, or has photoevaporation stripped that away, leaving only a secondary atmosphere or water vapor? HD 3167 is an older, less active star than many planet hosts, so photoevaporation should be less intense. But has it been enough to strip atmospheres over billions of years? By determining HD 3167c's atmospheric composition, we learn about the conditions under which planets retain or lose atmospheres, crucial for understanding which planets can maintain habitable conditions. 2. Water worlds and volatile delivery. If HD 3167c turns out to be water-rich, it would confirm that substantial volatile delivery, water and other ices, can occur even in inner regions of planetary systems. This has implications for how planets like Earth acquired their water. Understanding water-rich planets helps us understand the pathways by which terrestrial planets become habitable, where water comes from, how it's retained, what determines whether planets end up dry like Mars or ocean-covered. 3. Super-Earth/mini-Neptune transition. HD 3167c sits right at the upper edge of the Radius Valley. Is it a large rocky planet or a small gaseous one? Answering this helps calibrate our understanding of where the transition occurs and what determines planetary type. Models of planetary population synthesis, computer simulations of how planets form and evolve, make predictions about this transition. HD 3167c provides an observational test of these models. 4. Multi-planet system architecture. HD 3167 isn't just one planet. It's 3 planets that form from the same protoplanetary disk, experienced the same stellar evolution, but ended up with different properties. HD 3167b, 1.7R, rocky, very hot. HD 3167c, 2.7R, ambiguous composition, warm. HD 3167d, non-transiting, possibly similar to C. Why are they so different? What determined their final masses, compositions, and orbits? Comparative studies of all 3 planets reveal system formation and evolution pathways. Section 7. Future observations. HD 3167c's story is just beginning. What's next? James Webb Space Telescope. HD 3167c is scheduled for JWST observations as part of multiple observing programs. Over the next few years, JWST will observe several transits across different wavelength ranges. Expected results: definitive atmospheric composition, detection or non-detection of H2, H2O, CH4, CO, CO2, atmospheric metallicity measurement, cloud/haze characterization. Answer: is it rocky plus atmosphere, or water world, or mini Neptune? Extremely large telescopes. The next generation of ground-based telescopes will have unprecedented capabilities. 30 to 40 meter primary mirrors. High-resolution spectroscopy. Could detect individual molecular absorption lines. Measure wind speeds through Doppler shifts. Characterize atmospheric 3D structure. Looking further ahead, proposed missions could take HD 3167C studies even further. Atmospheric remote sensing infrared exoplanet large survey, or aerial. ESA mission launching 2029 will characterize 1,000 exoplanet atmospheres, including HD 3167C. Habitable Worlds Observatory, in 20 or more years, could directly image HD 3167C, separating its light from the star. Next-generation radio telescopes could detect magnetic fields, aurorae. Long-term monitoring over decades might reveal atmospheric variability or weather patterns. Seasonal changes if atmosphere is dynamic. Transit timing variations indicating additional planets. Orbital evolution over time. HD 3167C represents the near future of exoplanet science. Within the next 5 to 10 years, we'll know what this planet is made of, what's in its atmosphere, and what that tells us about planetary formation and evolution. And that knowledge will guide the search for habitable worlds for decades to come. Let's wrap up what we've learned. 154 light-years away, HD 3167C continues its month-long orbit around an orange dwarf star. Is it a rocky super-Earth with a thick atmosphere? A water world with global steam oceans? A mini Neptune with hydrogen-helium skies? We don't know yet, but we're about to find out. HD 3167C represents something profound. We're at the point where we can actually characterize the atmospheres of rocky-ish planets around other stars. Not just detect them, not just measure their sizes and masses, but actually determine what they're made of and what's in their atmospheres. Every technique we develop, every observation we make, every piece of knowledge we gain from planets like HD 3167C brings us closer to the ultimate goal: finding and confirming life on planets orbiting distant stars. HD 3167C isn't habitable itself, but understanding it is a critical step toward identifying worlds that are. For our next world, let's head on over to WASP 88b, a hot Jupiter revealing atmospheric secrets. 660 light-years from Earth, a gas giant nearly twice Jupiter's size races around its star every 4 days. Temperatures exceed 1,700 Kelvin, hot enough to vaporize metals. And its atmosphere, studied by astronomers worldwide, reveals clouds that shouldn't exist at such extreme temperatures. This is WASP 88b, a hot Jupiter teaching us that exoplanet atmospheres are far more complex and mysterious than we ever imagined. Hey everyone, welcome back to the channel. Today we're exploring WASP 88b, a hot Jupiter that's challenging our understanding of exoplanet atmospheres by showing us that even at scorching temperatures, clouds can form and dramatically affect what we observe. When we discover exoplanets, the first questions are always, how big is it? How massive? What's its temperature? But increasingly, astronomers are asking deeper questions. What's in its atmosphere? Are there clouds? What does the atmospheric composition tell us about how the planet formed and evolved? Exoplanet atmospheres are windows into planetary science. They reveal formation histories, chemical compositions, and the physical processes operating on worlds vastly different from anything in our solar system. But observing these atmospheres is challenging. Most planets are too faint, their signals too weak, their host stars too dim. WASP 88b is different. Discovered in 2014 by the WASP survey, this planet orbits a relatively bright star, magnitude 10.9, making it accessible for detailed atmospheric studies. And what astronomers have found is fascinating. Evidence for high-altitude clouds that shouldn't exist according to simple models, but clearly do. WASP 88b isn't just another hot Jupiter. It's a laboratory for understanding atmospheric physics under extreme conditions. Temperatures where silicates vaporize, where chemistry operates in regimes we can't replicate on Earth, where clouds form from materials that would be rocks on Earth's surface. Today we're going to explore how WASP 88b was discovered by the WASP project, what makes its physical characteristics noteworthy, the atmospheric mysteries that have astronomers intrigued, why studying cloudy atmospheres matters for exoplanet science, and what future observations might reveal. Let's get started. Section 1. The WASP project. To understand WASP 88b's discovery, we need to talk about one of the most successful ground-based planet hunting projects, the wide-angle search for planets. WASP began operations in 2004 with a simple but powerful concept. Use arrays of relatively small, wide-field cameras to monitor hundreds of thousands of stars simultaneously, searching for the periodic dimming that indicates a transiting planet. WASP consists of two facilities: Super WASP North on La Palma in the Canary Islands, Super WASP South at the South African Astronomical Observatory. Together, they monitor both northern and southern skies, maximizing coverage and discovery potential. Each WASP facility uses 8 cameras with 200mm lenses, essentially high-end camera lenses mounted on robotic systems. Each camera covers about 64 square degrees of sky. For comparison, the full moon covers about 0.5 square degrees, so each WASP camera monitors an area 128 times larger. By the time WASP 88b was discovered in 2014, the WASP project had already found over 100 exoplanets, with many more candidates being confirmed. The project has been remarkably successful at finding hot Jupiters, large gas giants in very close orbits, because these planets create the largest transit signals and are easiest to detect. WASP's strategy is breadth over depth. Monitor as many stars as possible with modest precision, rather than monitoring fewer stars with extreme precision like space missions do. This approach works excellently for finding large planets around relatively bright stars, exactly the targets best suited for follow-up atmospheric studies. WASP 88b is one of hundreds of planets discovered through this systematic survey, a testament to the power of persistent, long-term monitoring of large numbers of stars. Section 2. The Discovery. Between 2006 and 2012, WASP South accumulated observations of a star cataloged as 1 SWASP, later designated WASP 88. The automated pipeline detected periodic transit signals occurring every 4.95 days. The transits showed depth about 1.2% dimming, indicating a large planet. Duration, approximately 3 hours. Period, 4.954 days, very consistent. Shape, classic transit profile, suggesting a genuine planet. Let's review how the transit method works, because understanding this is key to knowing what we learn about WASP 88b. When a planet passes in front of its star from our perspective, it blocks a fraction of the star's light proportional to the planet's cross-sectional area. For WASP 88b, which has a radius about 1.7 times Jupiter's, the transit blocks approximately 1.2% of the star's light. From this transit signal, astronomers measure planet radius from how much light is blocked, orbital period from how often transits occur, orbital geometry from transit duration and shape, stellar properties combined with spectroscopy. But detecting a transit signal isn't enough to confirm a planet. WASP 88 required extensive follow-up. High-resolution imaging verified no nearby companion stars, creating false positives. Spectroscopic observations characterize the host star's properties: temperature, mass, composition, age. Radial velocity measurements detected the star's wobble induced by the planet's gravity, confirming its mass. The radial velocity observations were crucial. They revealed that WASP-88b has a mass of approximately 0.56 Jupiter masses, about 56% of Jupiter's mass. Combined with a radius of 1.70 Jupiter radii from transits, this gives a density of about 0.14 g/cm superscript 3, extremely low, indicating a highly inflated planet. WASP-88b was announced in 2014 as part of a paper describing multiple WASP discoveries. Immediately, its combination of relatively bright host star, magnitude 10.9, and large size made it a candidate for atmospheric characterization studies. Section 3. Characteristics of WASP-88b. Let's break down what WASP-88b actually is. Classification: Hot Jupiter. WASP-88b is a classic hot Jupiter, a gas giant orbiting extremely close to its star with a scorching temperature. Physical characteristics: radius 1.70 Jupiter radii, 70% larger than Jupiter. Mass 0.56 Jupiter masses, 56% of Jupiter's mass. Density 0.14 g/cm superscript 3, about 1/10 Jupiter's density. That density of 0.14 g/cm superscript 3 is extraordinarily low, about the density of balsa wood, and much less dense than Saturn, 0.69 g/cm superscript 3, which is often cited as the least dense planet in our solar system. WASP-88b is highly inflated by intense stellar heating. Inside WASP-88b, we probably have a small rocky/icy core, perhaps 10 to 20 Earth masses. Metallic hydrogen at high pressures deeper down. Molecular hydrogen transitioning to atomic hydrogen. A hot, extended atmosphere heated by the nearby star. The extreme inflation means the planet's mass is spread over a much larger volume than it would be in a cold orbit, creating this puffy structure. Orbital characteristics. Period, 4.954 days. Distance, 0.0563 AU. Comparison. About 7 times closer than Mercury orbits the Sun. At this close distance, WASP-88b is certainly tidally locked. One hemisphere permanently faces the star, the other in eternal darkness. The orbital velocity is approximately 130 kilometers per second, nearly 300,000 miles per hour. Temperature. WASP-88b's equilibrium temperature is estimated at approximately 1,740 Kelvin. At these temperatures, atmospheric dynamics are extreme. Supersonic winds racing at several kilometers per second. Day-night temperature contrasts of hundreds of Kelvin. Vigorous vertical mixing and circulation. Chemical reactions operating at extreme rates. That magnitude of 10.9 is important. It's bright enough for detailed spectroscopic studies, making WASP-88b one of the better targets for atmospheric characterization. Section 4. The cloudy atmosphere. What makes WASP-88b particularly interesting isn't just its size or temperature. It's what astronomers have discovered about its atmosphere. Several teams have observed WASP-88b using transmission spectroscopy, a technique where you observe the planet's transit at multiple wavelengths and look for atmospheric absorption features. Here's how it works. As the planet transits, some starlight passes through the planet's atmosphere before reaching us. Different molecules in the atmosphere absorb light at different wavelengths, creating a spectral fingerprint that reveals atmospheric composition. For a hot Jupiter at 1,740 K, models predict strong absorption features for molecules like water vapor, sodium, potassium, possibly carbon monoxide, and other species. But when astronomers observed WASP-88b, they found something unexpected. The spectral features were much weaker than predicted. The transmission spectrum was relatively flat across multiple wavelengths. A flat or muted transmission spectrum typically means one thing: clouds or hazes. High-altitude clouds act like a blanket, blocking our view of the deeper atmosphere where molecular absorption occurs. Instead of seeing through to various atmospheric levels and detecting molecules, we just see the top of the cloud deck, giving a featureless, flat spectrum. This discovery is scientifically important for several reasons. 1. Clouds at extreme temperatures. At 1,740 K, most materials we think of as cloud particles would be gaseous. What could form clouds at such high temperatures? Possibilities include silicate clouds, compounds like instatite or forsterite that are rocks on Earth but can form tiny droplets or particles at 500-800 K. Iron/metal clouds, metallic iron or titanium compounds vaporizing on the hot day side and condensing on the cooler night side. Corundum, aluminum oxide, essentially tiny sapphire/ruby particles floating in the atmosphere. Photochemical hazes, complex organic molecules or sulfur compounds created by stellar UV radiation. The exact composition depends on temperature, pressure, and atmospheric circulation. On WASP-88b, clouds might form on the cooler night side and be transported by winds to the day side, where they eventually evaporate. 2. Atmospheric circulation patterns. The presence and distribution of clouds tells us about atmospheric dynamics, how winds redistribute heat, where convection occurs, how the day-night temperature difference drives circulation. If clouds cover the entire planet uniformly, it suggests very vigorous mixing. If clouds are patchy or exist only at specific latitudes or longitudes, it reveals more complex circulation patterns. 3. Challenges for atmospheric characterization. Cloudy atmospheres make it much harder to determine composition. You can't measure molecules you can't see through the clouds. This is one of the biggest challenges in exoplanet atmospheric science right now. Many planets, maybe most, have cloudy or hazy atmospheres. Developing techniques to characterize these atmospheres despite the clouds is a major research frontier. Observations of WASP-88b have included ground-based spectroscopy detecting sodium but with muted features suggesting clouds. Hubble Space Telescope observations constraining water vapor abundance and cloud properties. Photometric monitoring searching for atmospheric variability. Some observations have detected weak sodium absorption, indicating that while clouds are present, they're not completely opaque at all wavelengths. This suggests either patchy clouds with clear regions or a partial cloud deck that allows some molecular features to be visible. Section 5. Why it matters. So why does WASP-88b matter? What does one cloudy, hot Jupiter teach us? WASP-88b contributes to several critical areas of exoplanet science. 1. Understanding atmospheric physics under extreme conditions. Hot Jupiters like WASP-88b operate in temperature and pressure regimes we can't replicate in laboratories. They're natural experiments testing atmospheric physics at extremes. By studying which materials form clouds at different temperatures, how those clouds affect observations, and how atmospheric circulation works under extreme heating, we learn fundamental physics applicable to any planetary atmosphere. 2. Cloud prevalence among exoplanets. Studies suggest that most exoplanets have cloudy or hazy atmospheres. WASP-88b is part of building statistics on which planets have clouds, what determines cloud coverage, how clouds correlate with temperature, gravity, atmospheric composition. Understanding the cloud patterns across many planets helps us predict which planets will have clear atmospheres suitable for detailed characterization, crucial for prioritizing observations with limited telescope time. 3. Planetary inflation mechanisms. WASP-88b's extremely low density, 0.14 g/cm superscript 3, and large radius make it one of the most inflated hot Jupiters known. What causes this extreme inflation? Theories include ohmic dissipation, atmospheric winds generating heat through interaction with magnetic fields, breaking gravity waves depositing energy at depth, direct radiative heating penetrating deep into the atmosphere. WASP-88b serves as a test case for these theories. Its extreme inflation suggests energy is being very efficiently deposited deep in the interior. 4. Comparative exoplanetology. By comparing WASP-88b to other hot Jupiters at similar temperatures, we identify patterns, which have clear atmospheres versus cloudy. How stellar properties affect planetary atmospheres. Whether cloud coverage correlates with other parameters. Each planet teaches us something, but patterns across many planets reveal the underlying physics governing all exoplanets. Section 6. Future observations. What's next for WASP-88b? What can future observations tell us? James Webb Space Telescope. JWST represents a transformational capability for studying exoplanet atmospheres, including cloudy ones like WASP-88b. JWST advantages. Extended wavelength range, 0.6 to 28 microns, sees where clouds might be more transparent. Higher sensitivity, detects fainter spectral features. Better spectral resolution, distinguishes overlapping molecular lines. Multiple instruments, NIR SPEC, NIRIS, MIRI, each offer different capabilities. For WASP-88b, JWST could detect molecular features through clouds at infrared wavelengths where cloud opacity is lower. Constrain cloud composition by measuring which wavelengths are affected. Measure atmospheric metallicity, the abundance of elements heavier than helium. Detect thermal emission during eclipse, revealing dayside temperature and heat redistribution. Extremely large telescopes. The next generation of ground-based telescopes, 30 to 40 meter class, will have unprecedented capabilities. High-resolution spectroscopy capable of detecting individual molecular lines. Ability to measure Doppler shifts from atmospheric winds. Direct detection of day-night atmospheric differences. Potential to track cloud formation and dissipation in real time. Continued monitoring. Long-term observations over years might reveal atmospheric variability. Do clouds come and go? Are there weather patterns? Orbital evolution. Is tidal dissipation causing orbital decay? Transit timing variations. Are there additional planets in the system? Even if WASP-88b isn't extensively observed individually, it contributes to population studies. By observing many hot Jupiters with similar properties, astronomers identify trends and test theories statistically. Looking further ahead, proposed missions like Aerial Atmospheric Remote Sensing Infrared Exoplanet Large Survey, launching in the late 2020s, will systematically characterize hundreds of exoplanet atmospheres, including WASP-88b, building comprehensive statistics on atmosphere properties across diverse planet types. Conclusion: 660 light-years away, WASP-88b continues its rapid orbit, completing a year every 5 Earth days. One hemisphere eternally faces a blazing star, heated to temperatures where rocks begin to soften. The other knows only darkness, cooled by atmospheric winds redistributing heat. And throughout its atmosphere, clouds form, perhaps silicate droplets, perhaps metallic particles, perhaps exotic compounds we've never encountered. These clouds shroud the planet, hiding its deeper secrets, challenging astronomers to develop new techniques to see through them. WASP-88b reminds us that exoplanets are complex, that atmospheres don't follow simple predictions, that nature is more creative than our models. The clouds that frustrate our observations also reveal profound physics, telling us about circulation patterns, chemical processes, energy transport in extreme environments. Every cloudy planet we characterize brings us closer to understanding atmospheric diversity across the galaxy. Every technique we develop to see through clouds prepares us for studying potentially habitable worlds, which might also have clouds hiding their surfaces. Let's keep the theme going and keep the mood light with KLT-11b, the Styrofoam planet. 320 light-years from Earth, a planet exists that defies everything we thought we knew about gas giants. It's 5 times Jupiter's size, but weighs barely more than Jupiter. Its density? 0.08 grams per cubic centimeter. Literally less dense than styrofoam, lighter than cork, a cosmic balloon inflated to impossible proportions. This is KLT-11b, one of the most extreme planets ever discovered, and it's forcing scientists to completely rethink what's possible in planetary physics. We're exploring one of the most bizarre and scientifically fascinating exoplanets ever discovered. KLT-11b, a planet so inflated, so low in density, that if you could somehow place it in a cosmic ocean, it would float. How does a planet, an object with the mass of Jupiter, becomes so bloated, so expanded, that it has the density of packing material? What physical processes could create such an extreme object? And what does KLT-11b teach us about the diversity of planets filling our galaxy? KLT-11b was discovered in 2016 by the KLT Survey, a project specifically designed to find bright exoplanet systems suitable for detailed follow-up studies. And KLT-11b didn't disappoint. It's not just extremely low density. It also orbits one of the brightest stars hosting a transiting exoplanet, making it perfect for atmospheric characterization. Today we're going to explore how KLT-11b was discovered by small ground-based telescopes, what makes its physical properties so extreme, why it's so incredibly inflated, and what that tells us about planetary physics, what scientists have learned about its atmosphere, and why this bizarre world matters for understanding exoplanets. Let's dive into the world of the Styrofoam planet. Section 1. The Kelp Project. To understand KLT-11b, we first need to understand the project that discovered it, KLT, which stands for Kilo Degree Extremely Little Telescope. KLT is actually 2 telescopes, KLT North at Weiner Observatory in Arizona and KLT South at the South African Astronomical Observatory. Despite the name calling them extremely little, they're not actually that small. They use 42mm camera lenses, essentially high-end telephoto lenses. What makes KLT unique is its strategy. Each telescope monitors an enormous area of sky, about 26 degrees by 26 degrees per pointing, which is roughly 676 square degrees, hundreds of times larger than the full moon's apparent size. Kelp's philosophy is breadth over depth. Rather than staring at a small patch of sky with extreme precision like Kepler did, KLT monitors huge areas with modest precision, focusing specifically on bright stars, magnitude 8 to 10, where follow-up observations are easiest. This approach is perfect for finding planets around bright stars, exactly the targets needed for detailed atmospheric studies. KLT can't find Earth-sized planets like Kepler could, but it excels at finding large, transiting planets around stars bright enough for spectroscopic characterization. By the time KLT-11b was discovered in 2016, KLT had found dozens of exoplanets, many of which became targets for atmospheric observations. But KLT-11b stood out immediately as something extraordinary. KELT's success demonstrates that you don't need enormous, expensive telescopes or space missions to make important discoveries. With clever design, patient observation, and the right strategy, even modest ground-based instruments can revolutionize our understanding of exoplanets. Section 2. The Discovery. Between 2006 and 2012, KLT North accumulated thousands of observations of a magnitude 8.0 star cataloged as TYC 3239-01327-1, later designated KLT 11. The KLT pipeline detected periodic dimming every 4.74 days with a depth of approximately 5%, an enormous transit signal. For comparison, Jupiter transiting the Sun blocks about 1% of light. A 5% transit meant something huge was passing in front of KLT-11. That 5% transit depth immediately flagged KLT-11b as unusual. Even for hot Jupiters, which are typically inflated, 5% is exceptionally large. It suggested either an extremely large planet or a planet orbiting a very small, dim star. Confirming KLT-11b required extensive follow-up observations from multiple facilities. High-resolution imaging verified KLT-11 is a single star with no close companions. Spectroscopic observations characterized the host star's properties, revealing it's actually an evolved subgiant star. Radial velocity measurements detected the planet's gravitational influence, measuring its mass. Additional transit observations refined the planet's size and orbital parameters. The radial velocity measurements revealed KLT-11b has a mass of approximately 0.195 Jupiter masses, about 20% of Jupiter's mass, or roughly 60 Earth masses. But the transit observations showed something shocking. KLT-11b has a radius of approximately 1.37 Jupiter radii, 37% larger than Jupiter. When you combine these measurements, mass 0.195 mj, 20% of Jupiter, radius 1.37 rj, 137% of Jupiter. The calculated density is approximately 0.08 g/cm superscript 3. When KLT-11b was announced in 2016, it immediately became one of the lowest density exoplanets ever discovered, earning it the nickname the Styrofoam Planet. But the extreme density was just the beginning of its story. Section 3. Characteristics of KLT-11b. Let's break down exactly what KLT-11b is and why it's so extreme. Classification: ultra-low density hot Jupiter. KLT-11b is classified as a hot Jupiter, but it's at the absolute extreme of the hot Jupiter population, one of the most inflated planets we've ever found. That density of 0.08 g/cm superscript 3 means KLT-11b's mass is spread over such an enormous volume that the planet is essentially a cosmic balloon. If you could stand on KLT-11b, which you can't because it's gas, you'd weigh only 1/10 what you weigh on Earth despite the planet's Jupiter-like mass. What's inside KLT-11b? Based on models, small rocky/icy core, perhaps 10 to 20 Earth masses at the center, metallic hydrogen, a high pressure is deep down, molecular hydrogen, transitioning to atomic hydrogen, extremely extended atmosphere, hundreds to thousands of kilometers deep before reaching solid interior. The atmosphere is so extended that the planet essentially is atmosphere. There's no clear boundary between atmosphere and interior. It's all gas with gradually increasing density toward the center. KLT-11b orbits about 8 times closer to its star than Mercury orbits the Sun. At this distance, it's certainly tidally locked. One hemisphere always faces the star. Temperature. KLT-11b's equilibrium temperature is estimated at approximately 1,700 to 1,800 Kelvin. That's hot enough to vaporize most metals, dissociate many molecules, create vigorous atmospheric dynamics, drive the extreme inflation we observe. Host star, KLT-11. Here's where things get even more interesting. KLT-11 isn't a normal main sequence star like our Sun. It's an evolved subgiant star. KLT-11 has exhausted hydrogen in its core and is evolving off the main sequence, beginning to expand into a subgiant. Eventually, it will become a red giant, potentially engulfing KLT-11b in the process. This raises a fascinating question. How long has KLT-11b been this inflated? Did the planet become extremely inflated only recently as the star evolved and brightened? Or has it always been this puffy? We don't know for certain, but studying KLT-11b might reveal how planets respond to their star's evolution. Section 4. Why so inflated? Okay, the big question, how does a planet become this inflated? What physical process creates a density of 0.08 g/cm superscript 3? The basic answer is stellar heating. KLT-11b receives enormous amounts of energy from its nearby star, thousands of times more than Jupiter receives from the Sun. This energy has to go somewhere. Normally, a gas giant planet would gradually contract under its own gravity, becoming denser over billions of years. Jupiter is still contracting very slowly even after 4.5 billion years. But when a gas giant orbits very close to a star, stellar heating can prevent this contraction or even drive expansion. For extreme inflation like KLT-11b's, scientists propose several mechanisms working together. 1. Ohmic dissipation. Atmospheric winds, driven by the day-night temperature contrast, interact with the planet's magnetic field. This creates electrical currents that dissipate as heat deep in the interior, maintaining elevated temperatures that prevent contraction. Think of it like electromagnetic braking. The moving conductive gas is slowed by magnetic fields, and that kinetic energy becomes heat. This heat, deposited at depth, maintains interior temperatures high enough that the planet can't contract. 2. Braking gravity waves. Temperature contrasts drive atmospheric waves, similar to waves in Earth's atmosphere, but far more extreme. These waves propagate downward and break at certain depths, depositing their energy as heat. It's like ocean waves breaking on a beach. The kinetic energy of a wave is converted to heat and turbulence. On KLT-11b, this happens continuously throughout the atmosphere, maintaining internal temperatures. 3. Enhanced opacity. If the atmosphere has materials that block infrared radiation very effectively, heat can't escape easily. This greenhouse effect, though not quite the same as Earth's greenhouse effect, can maintain elevated temperatures throughout the envelope. Most likely, all three mechanisms contribute to KLT-11b's extreme inflation. The combination of ohmic dissipation, wave breaking, and enhanced opacity maintains interior temperatures hundreds or thousands of Kelvin above what they'd be without heating, preventing gravitational contraction and maintaining the extreme low density we observe. But here's the puzzle. Many hot Jupiters receive similar or even higher stellar flux than KLT-11b, yet they're not as inflated. Why is KLT-11b so extreme? Possible explanations. Low mass. At only 0.195 Jupiter masses, KLT-11b has weaker gravity, making it easier to inflate. Stellar evolution. The evolving subgiant host may have recently increased in brightness, catching the planet in a transitional phase. Atmospheric composition. Perhaps KLT-11b has unusually high metallicity or specific compounds that enhance heating efficiency. Internal structure. Maybe it has an unusually small core, allowing more expansion. We don't fully understand why KLT-11b is so extreme, and that's exactly why it's so scientifically valuable. This planet is testing the limits of our inflation models, showing us conditions we hadn't fully accounted for. Section 5. Atmospheric Studies. KLT-11b's extreme size and bright host star make it perfect for atmospheric studies. When a planet this large transits a bright star, it creates enormous opportunities for transmission spectroscopy, observing how the planet's atmosphere absorbs starlight at different wavelengths to determine what molecules are present. KLT-11b's extremely low gravity, 0.10 g, means its atmospheric scale height, how quickly density decreases with altitude, is very large. A large scale height means atmospheric features are more prominent and easier to detect. Multiple teams have observed KLT-11b's atmosphere. Ground-based spectroscopy has detected sodium, clear detection in optical wavelengths; potassium, tentative detection, evidence for relatively clear atmosphere, not heavily clouded. Hubble Space Telescope observations revealed water vapor, H2O detected in near-infrared. Atmospheric structure, evidence for temperature inversions, hotter upper atmosphere. Spitzer Space Telescope measured thermal emission during eclipse. Dayside temperature, approximately 2000 K. Heat redistribution, moderately efficient atmospheric circulation. These observations tell us several important things. KLT-11b has a hydrogen-helium-dominated atmosphere, as expected for a gas giant. Water vapor presence confirms volatiles survive despite extreme temperatures. Sodium and potassium detection suggests a relatively clear atmosphere without thick cloud decks blocking our view. Temperature inversion, if confirmed, could indicate absorbers like titanium oxide or vanadium oxide in the upper atmosphere. Moderate heat redistribution means atmospheric winds partially, but not completely homogenize day-night temperature differences. Models predict supersonic winds racing around the planet at 4 to 6 kilometers per second, transporting heat from the permanent day side to the night side. The weak gravity means these winds can be even faster than on more massive hot Jupiters, creating extremely dynamic, turbulent atmospheric conditions. KLT-11b's atmosphere is essentially an enormous, low-gravity laboratory where we can study atmospheric physics under conditions impossible to replicate on Earth or in our solar system. Section 6. Scientific Significance. Why does KLT-11b matter? What does one ultra-low density, hot Jupiter teach us? Significance number 1. Testing inflation models. KLT-11b's extreme inflation, density 0.08 g/cm superscript 3, pushes theoretical models to their limits. Any successful theory of planetary inflation must explain how a planet can become this inflated without flying apart under its own rotation or tidal forces. By comparing models to KLT-11b's observed properties, scientists refine theories about energy transport, atmospheric dynamics, and the conditions enabling extreme inflation. Significance number 2. Atmospheric characterization. KLT-11b is one of the best targets for atmospheric studies due to extremely large size, 1.37 RJ, creating strong signals. Bright host star, magnitude 8.0, providing ample photons. Low gravity, creating large atmospheric scale heights. Relatively clear atmosphere, allowing molecular detection. Studies of KLT-11b's atmosphere contribute to our understanding of how molecules behave at extreme temperatures, atmospheric chemistry in hydrogen-dominated envelopes, heat transport mechanisms in tidally locked planets, the effects of stellar evolution on planetary atmospheres. Significance number 3. planetary evolution. KLT-11's status as an evolved subgiant makes the system valuable for understanding how planets respond to their star's evolution. As stars age and brighten during their transition to red giants, close-in planets receive increasing stellar flux. KLT-11b might be showing us what happens when this process begins. Extreme inflation as the planet adjusts to its star's increased luminosity. In a few hundred million years, KLT-11 will expand into a full red giant, potentially engulfing KLT-11b. Is the extreme inflation we see today a precursor to the planet's eventual destruction? Studying this system helps us understand planetary systems' ultimate fates. Significance number 4. Diversity of planetary systems. KLT-11b reminds us that planets can exist in states and configurations we never predicted. Densities below 0.1 g/cm superscript 3 weren't seriously considered possible before planets like KLT-11b were discovered. Every extreme planet we discover expands our understanding of what's possible, what conditions planets can endure, what forms they can take, how diverse planetary systems truly are. Section 7. Future Observations. What's next for KLT-11b? James Webb Space Telescope. KLT-11b is an excellent JWST target due to its large size, bright host star, and frequent transits. JWST could detect additional molecules, measure atmospheric metallicity precisely, constrain temperature-pressure structure throughout the atmosphere, detect temperature inversions definitively, search for atmospheric variability or weather. With JWST's sensitivity and wavelength coverage, scientists hope to understand exactly what's causing the extreme inflation, determine if special atmospheric composition contributes, measure heat redistribution efficiency precisely, test planetary inflation theories comprehensively. Long-term studies, continued monitoring of KLT-11b over years or decades could reveal atmospheric variability. Does the atmosphere change over time? Orbital decay. Is tidal friction causing the orbit to shrink? Stellar evolution effects. Is the planet becoming more inflated as the star evolves? Transit timing variations. Are there additional planets in the system? Even if KLT-11b isn't observed extensively by every new facility, it contributes to comparative studies. By analyzing many hot Jupiters across different inflation levels, scientists identify the factors that determine which planets become extremely inflated. Conclusion: 320 light-years away, KLT-11b continues its rapid orbit around an aging star. Every 4.74 days, every 114 hours, the planet completes another year, one hemisphere baked by intense stellar radiation, the other cooled by darkness and winds. This cosmic balloon, with density less than cork, defies intuition. How can an object with Jupiter's mass be spread across such an enormous volume? How can gravity be so weak, atmospheric scale heights so large, inflation so extreme? We don't have all the answers yet. KLT-11b remains somewhat mysterious. Its extreme inflation not fully explained by current models, its atmospheric composition still being characterized, its future fate as its star evolves uncertain. But that's exactly what makes KLT-11b so valuable. This planet pushes the boundaries of planetary science, shows us conditions we hadn't imagined, tests our theories to breaking points. Every observation reveals new complexity. Every model comparison raises new questions. Planets like KLT-11b remind us that the universe is far stranger and more diverse than we can predict. Before exoplanets, we thought hot Jupiters couldn't exist. Now we found thousands. Before KLT-11b, we didn't think planets could have densities this low. Now we know they can. For our next world, we're warping over to WASP 106b, a hot Jupiter revealing gas giant diversity. 460 light-years from Earth, a gas giant races around its star every 9 days. It's slightly larger than Jupiter, moderately inflated by stellar heating, and its atmosphere contains secrets about how gas giants form and evolve across the galaxy. This is WASP 106b, not the most extreme hot Jupiter, not the largest or the hottest, but precisely because it's typical, it's scientifically invaluable. This planet represents what hot Jupiters are actually like across the galaxy. WASP 106b, a hot Jupiter that might not break records, but that's exactly what makes it so important for understanding the diversity of gas giant planets orbiting stars throughout our galaxy. When we discover exoplanets, it's easy to focus on the extremes, the hottest, the largest, the closest, the most unusual. But understanding the full population of planets requires studying the typical, the representative, the normal cases. And that's where WASP 106b comes in. WASP 106b sits firmly in the middle of the hot Jupiter distribution. It's moderately inflated, neither extremely puffy nor unusually compact. It orbits at a moderate distance for a hot Jupiter. Its temperature is high, but not extreme. It's what a typical hot Jupiter actually looks like. Discovered in 2016 by the WASP survey, WASP 106b immediately became valuable for comparative studies. By understanding planets like WASP 106b, the ones that represent the majority of the population, we learn about the processes that shape all gas giants. Today we're going to explore how WASP 106b was discovered and confirmed, what makes it a typical hot Jupiter, and why that matters. What we've learned about its atmosphere through observations, how it fits into the broader picture of gas giant diversity, and what future studies might reveal. Let's explore the world of the representative hot Jupiter. Section 1. The WASP Project. WASP 106b was discovered by the Wide-Angle Search for Planets, one of the most successful ground-based exoplanet surveys. WASP operates 2 facilities, Super WASP North on La Palma in the Canary Islands and Super WASP South at the South African Astronomical Observatory. Together, they've discovered over 200 exoplanets since operations began in 2004. WASP's strategy is to monitor huge areas of sky, hundreds of square degrees, looking for periodic dimming in bright stars that indicates transiting planets. The focus on bright stars, magnitudes of 7 to 13, ensures follow-up observations are feasible. By 2016, when WASP 106b was discovered, WASP had already found numerous hot Jupiters and built a statistical understanding of this planetary class. WASP 106b added to this data set one more data point helping define what hot Jupiters are truly like. Understanding planetary populations requires many examples. Individual extreme cases are interesting, but patterns across hundreds of planets reveal the underlying physics. WASP 106b contributes to these population studies, helping scientists identify which properties are common, which are rare, and what processes determine planetary characteristics. Section 2. The Discovery. Between 2006 and 2013, WASP South accumulated observations of a star cataloged as 1SWASP, later designated WASP 106. The automated pipeline detected periodic transit signals every 9.3 days. The transit method works by detecting the tiny dimming when a planet passes in front of its star from our perspective. For WASP 106b, which has a radius about 1.09 times Jupiter's orbiting a Sun-like star, the transit blocks approximately 1.3% of the star's light, clearly detectable with WASP cameras. Confirming WASP 106b required follow-up from multiple observatories. High-resolution imaging verified WASP 106 is a single star without close companions that could create false positive signals. Spectroscopic observations characterized the host star, measuring its temperature, mass, composition, and evolutionary state. Radial velocity measurements detected the gravitational wobble induced by the planet, confirming its mass. The radial velocity observations measured WASP-106b's mass at approximately 1.925 Jupiter masses, nearly twice Jupiter's mass. Combined with a radius of 1.085 Jupiter radii from transits, this gives a density of about 1.45 g/cm superscript 3, moderately inflated compared to Jupiter's 1.33 g/cm superscript 3, but not extremely so. WASP-106b was announced in 2016 as part of a paper describing multiple WASP discoveries. While not the most extreme planet discovered that year, it immediately joined the catalog of well-characterized hot Jupiters suitable for atmospheric studies. Section 3. Characteristics of WASP-106b. Let's examine WASP-106b's characteristics in detail. Classification: moderately inflated hot Jupiter. WASP-106b is a classic hot Jupiter, a gas giant in a very close orbit with elevated temperature, but it's not at the extreme end of any particular characteristic. It's representative of the typical hot Jupiter population. That density of 1.45 g/cm superscript 3 places WASP-106b in the moderately inflated category. It's expanded by stellar heating, about 8.5% larger than Jupiter despite being more massive, but it's not extremely inflated like some hot Jupiters that have densities below 0.5 g/cm superscript 3. Inside WASP-106b, models predict a small rocky/icy core, 10 to 30 Earth masses, metallic hydrogen layer under extreme pressure, molecular hydrogen transitioning to atomic hydrogen, hot, extended atmosphere heated by the nearby star. WASP-106b orbits about 4 times closer to its star than Mercury orbits the Sun. This places it firmly in the hot Jupiter regime, but not at the extreme close distances, 0.01 to 0.03 AU, seen in ultra-hot Jupiters. At 0.092 AU, it's in the middle of the hot Jupiter distribution. WASP-106b's equilibrium temperature is estimated at approximately 1,500 to 1,600 Kelvin. This is hot enough that water exists only as steam. Many metals are vaporized. Silicate compounds can form clouds. Atmospheric chemistry is complex and dynamic. At this orbital distance, WASP-106b is certainly tidally locked. One hemisphere permanently faces the star while the other remains in darkness. Atmospheric winds redistribute heat, though not completely, creating a day-night temperature gradient. While magnitude 11.9 is too faint for naked eye viewing, it's bright enough for detailed spectroscopic studies, making WASP-106b accessible for atmospheric characterization. Section 4. Atmospheric Studies. WASP-106b's moderate size, relatively bright host star, and frequent transits make it suitable for atmospheric studies. Multiple teams have observed WASP-106b using transmission spectroscopy, measuring how the planet's atmosphere absorbs starlight at different wavelengths during transits to determine atmospheric composition. When WASP-106b transits, starlight passes through its atmosphere before reaching us. Different molecules absorb light at characteristic wavelengths, creating spectral signatures that reveal what's in the atmosphere. Observations of WASP-106b have revealed sodium in a clear detection in optical wavelengths, one of the most common features detected in hot Jupiter atmospheres. Water vapor, H2O tentative detection in near-infrared, though observations are challenging. Atmospheric haze/clouds, some evidence for high-altitude aerosols that mute spectral features. These observations tell us WASP-106b has a hydrogen-helium atmosphere, expected for a gas giant. Sodium presence indicates temperatures and pressures where sodium can exist in atomic form in the upper atmosphere. Possible haze/clouds suggest photochemistry or condensates forming at high altitudes. Water vapor detection, if confirmed, indicates volatiles survive despite high temperatures. Models of WASP-106b's atmosphere predict: upper atmosphere, atomic species, sodium, potassium, possible hazes. Mid-atmosphere, molecular species, water, carbon monoxide, possible clouds. Deep atmosphere, increasing pressure and temperature, transition to liquid/metallic phases. The day-night temperature difference drives supersonic winds, likely 2 to 4 kilometers per second, redistributing heat around the planet. These winds create complex circulation patterns with equatorial jets and high-latitude vortices. What's scientifically valuable about WASP-106b's atmosphere is its typicality. Some hot Jupiters have extremely clear atmospheres, showing strong molecular features. Others are heavily clouded, hiding atmospheric composition. WASP-106b appears to be in between, moderately hazy but not completely opaque. By studying many hot Jupiters like WASP-106b, planets with moderate temperatures, moderate inflation, moderate atmospheric opacity, we learn what's common versus rare. This statistical understanding helps identify the physical processes operating across the population. WASP-106b isn't special because it's extreme, it's special because it's representative. Understanding this planet helps us understand what gas giants are typically like when they orbit close to their stars. Section 5. Scientific significance. Why does WASP-106b matter for exoplanet science? Significance number 1. Population studies. WASP-106b represents the typical hot Jupiter. Not the most extreme in any dimension, but sitting near the center of multiple distributions: mass, radius, temperature, orbital period. Studying typical cases reveals what processes are common versus what requires special conditions. By characterizing many planets like WASP-106b, scientists identify correlations. How does inflation depend on temperature and stellar flux? What determines atmospheric opacity, clear versus cloudy? How do atmospheric compositions vary with formation location? What fraction of hot Jupiters have various characteristics? Significance number 2. Testing formation and migration theories. Hot Jupiters like WASP-106b almost certainly didn't form where we find them. Gas giants need to form beyond the snow line, where ices exist, then migrate inward through disk migration, planet-planet scattering, or cosolitive oscillations. WASP-106b's properties constrain these theories. Its moderate density suggests it retains some volatiles during migration. Its nearly circular orbit favors disk migration over violent scattering. Its atmospheric composition might reveal formation location. Significance number 3. Atmospheric physics benchmarking. WASP-106b provides a test case for atmospheric models. Scientists predict what its atmosphere should look like based on temperature, pressure, stellar flux, and composition. Observations either confirm these predictions or reveal missing physics. When models match observations for planets like WASP-106b, we gain confidence in our understanding. When they don't match, we discover new physics, unexpected chemistry, surprising cloud behavior, unanticipated circulation patterns. WASP-106b is twice Jupiter's mass, but only 8.5% larger, denser than many hot Jupiters. Why? Comparing it to more inflated planets reveals what causes extreme inflation. Comparing it to more compact planets reveals what enables contraction despite intense heating. Section 6. Future research. What's next for WASP-106b? While WASP-106b might not be the highest priority JWST target, there are more extreme planets and brighter host stars. It could still be observed as part of broader surveys characterizing hot Jupiter atmospheres. JWST observations would answer: does WASP-106b have enhanced metallicity, suggesting formation far from the star? Are its clouds silicates, photochemical hazes, or something else? How efficiently do winds redistribute heat? Future extremely large telescopes, ELTs, with 30 to 40 meter mirrors will enable high-resolution spectroscopy, detecting individual molecular lines and measuring Doppler shifts from atmospheric winds. Even if WASP-106b isn't studied intensively as an individual target, it contributes to population surveys. Future missions will characterize hundreds of hot Jupiters, and WASP-106b represents the typical case against which extremes are compared. Alright, let's recap what makes WASP-106b scientifically important. 460 light-years away, WASP-106b continues its rapid orbit, completing a year every 9 days. One side baked by stellar radiation, the other cooled by darkness and winds. Sodium atoms floating in its upper atmosphere, clouds or hazes moderating spectral features, supersonic winds racing across its surface. This planet won't win awards for being the hottest, largest, or most unusual. But that's not why it matters. WASP-106b matters because it represents what hot Jupiters actually are, not the extremes that make headlines, but the typical cases that define the population. Science advances through studying both extremes and averages. Extremes test our theory's limits. Averages reveal what processes are common, what conditions are normal, what patterns define planetary populations. WASP-106b is one of hundreds of hot Jupiters we've discovered. Each one, whether extreme or typical, teaches us something about planetary formation, atmospheric physics, system dynamics, and the incredible diversity of worlds filling our galaxy. For our last world today, we're ending with a truly fascinating one. HAT P54b, a hot Jupiter from the HATnet survey. 560 light-years from Earth, a gas giant circles its star every 3.8 days. It's slightly larger than Jupiter, moderately inflated by stellar heating, and was discovered not by a space telescope, but by a network of small, automated telescopes on Earth. This is HAT P54b, discovered by the HATnet project, a remarkable program proving that you don't need billion-dollar space missions to revolutionize exoplanet science. Sometimes, ingenuity and persistence matter more than size. We're exploring HAT P54b, a hot Jupiter that represents the power of ground-based automated surveys in discovering and characterizing exoplanets around distant stars. When most people think about exoplanet discoveries, they imagine massive space telescopes like Kepler or James Webb. But some of the most successful planet hunting programs use networks of relatively small, automated telescopes right here on Earth. And HAT P54b is a perfect example of what these programs can achieve. The story of HAT P54b is really two stories. The story of the planet itself, a moderately inflated hot Jupiter orbiting a sun-like star, and the story of HATnet, a pioneering project that has discovered over 130 exoplanets using small telescopes, clever design, and persistent observation. Discovered in 2015, HAT P54b joins a catalog of hot Jupiters that have taught us about planetary formation, atmospheric dynamics, and the incredible diversity of worlds orbiting distant stars. Today we're going to explore how the HATnet project works and why it's been so successful, the discovery and confirmation of HAT P54b, what makes this planet scientifically interesting, what observations have revealed about its atmosphere, and what future studies might teach us. let's discover what small telescopes can achieve. Section 1. The HATNet Project. HAT P54b was discovered by HATNet, the Hungarian-made automated telescope network, one of the most successful ground-based exoplanet surveys. HATNet began operations in 2003, created by astronomers at the Harvard-Smithsonian Center for Astrophysics. The concept was elegantly simple. Use networks of small, fully automated telescopes to monitor thousands of stars simultaneously, searching for the periodic dimming that indicates transiting planets. Each HATNet telescope is remarkably modest. Aperture, 11 centimeters, about 4.3 inches. Lens, Canon telephoto lenses. Field of view, about 8 degrees square, over 60 square degrees. Cost, approximately $60,000 per telescope, compared to billions for space missions. That 60-plus square degree field of view is enormous. For comparison, the full moon appears about 0.5 square degrees. Each HATNet telescope monitors an area over 120 times larger. This wide coverage allows HATNet to survey hundreds of thousands of stars simultaneously. HATNet operates from multiple sites. HAT 5 through HAT 9, Fred Lawrence Whipple Observatory, Arizona. HAT 10, Mauna Kea Observatory, Hawaii. HAT South, extended network in Southern Hemisphere, Chile, Namibia, Australia. The observing strategy is systematic. Monitor thousands of stars each night. Detect periodic dimming using automated pipelines. Flag candidates for follow-up observations. Confirm with larger telescopes using radial velocity and high-resolution imaging. By 2015, when HAT P54b was discovered, HATNet had already found over 100 exoplanets, with discoveries continuing through the present. The project demonstrates that exoplanet science doesn't require enormous facilities. It requires smart design, persistent observation, and careful analysis. Here's a remarkable fact. HATNet's entire network cost less than $1 million to build and operate annually. Compare that to space missions costing billions. Yet HATNet has discovered more exoplanets than many larger projects. It's a testament to the power of well-designed ground-based surveys. Section 2. The Discovery. Between 2009 and 2011, HATNet telescopes in Arizona accumulated observations of a star cataloged as GSC 2949-0967, later designated HAT P54. The automated pipeline detected periodic transit signals. Period, 3.799 days, less than 4 days. Depth, approximately 1.5% dimming. Duration, about 2.5 hours. Shape, consistent with planetary transit. A 1.5% transit depth indicates a planet roughly the size of Jupiter orbiting a sun-like star. This immediately flagged HAT P54b as a hot Jupiter candidate, large gas giants in very close orbits. The transit method works by detecting the dimming when a planet passes in front of its star from our perspective. For HAT P54b, with a radius about 1.2 times Jupiter's, transiting a sun-like star, the transit blocks approximately 1.5% of the star's light, clearly detectable by HATNet's sensitive cameras. From transits alone, astronomers measure planet radius from dimming depth, orbital period from transit frequency, orbital distance from period using Kepler's laws, stellar properties combined with spectroscopy. Confirming HAT P54b required extensive follow-up from larger telescopes. High-resolution imaging from telescopes like the Keck Observatory verified HAT P54 is a single star without close companions that could create false signals. Spectroscopic observations characterize the host star's temperature, mass, composition, and evolutionary state. Radial velocity measurements from multiple observatories detected the star's wobble caused by the planet's gravity, confirming its mass. The radial velocity observations measured HAT P54b's mass at approximately 0.76 Jupiter masses, about 3/4 of Jupiter's mass. Combined with the radius of 1.19 Jupiter radii from transits, this gives a density of about 0.45 g/cm superscript 3, moderately inflated, less dense than Jupiter, 1.33 g/cm superscript 3, but not extremely so. HAT P54b was announced in 2015 in a paper published in the Astronomical Journal. It joined over 100 other HATnet discoveries, continuing the project's impressive track record of finding transiting exoplanets around bright stars suitable for detailed follow-up. Section 3. Characteristics of HAT P54b. Let's examine HAT P54b's characteristics in detail. Classification: moderately inflated hot Jupiter. HAT P54b is a classic hot Jupiter, a gas giant orbiting very close to its star with elevated temperature and moderate inflation from stellar heating. Physical characteristics: radius 1.19 Jupiter radii, about 19% larger than Jupiter. Mass 0.76 Jupiter masses, 76% of Jupiter's mass. Density 0.45 g/cm superscript 3, about 1/3 Jupiter's density. Surface gravity 0.90 times Jupiter's gravity. That density of 0.45 g/cm superscript 3 places HAT P54b in the moderately inflated category for hot Jupiters. It's less dense than Jupiter, but not extremely inflated like planets with densities below 0.2 g/cm superscript 3. The 19% radius inflation is consistent with stellar heating preventing gravitational contraction. Inside HAT P54b, models predict a small rocky/icy core, perhaps 10 to 20 Earth masses, metallic hydrogen under extreme pressure, molecular hydrogen atmosphere, extended outer layers heated by the nearby star. HAT P54b orbits about 8 times closer to its star than Mercury orbits the Sun. At this distance, the planet is certainly tidally locked, one hemisphere permanently facing the star, the other in perpetual darkness. Temperature: HAT P54b's equilibrium temperature is estimated at approximately 1,500 to 1,600 Kelvin. This temperature means water exists only as steam. Many metals are vaporized. Atmospheric chemistry is complex. Vigorous atmospheric circulation. Host star: HAT P54 GSE 2949-00967. HAT P54 is remarkably similar to our Sun. Same mass, same size, same temperature, similar age. This makes the system valuable for understanding how hot Jupiters behave around Sun-like stars, directly applicable to understanding planetary systems generally. Section 4. Atmospheric Studies. HAT P54b's properties: moderate size, bright host star, frequent transits, make it suitable for atmospheric characterization. Several teams have attempted atmospheric observations of HAT P54b using transmission spectroscopy, observing the planet's transit at multiple wavelengths to detect atmospheric absorption features. During transit, starlight passes through HAT P54b's atmosphere before reaching us. Different molecules absorb light at characteristic wavelengths, creating spectral signatures revealing atmospheric composition. HAT P54b faces some observational challenges. The host star at magnitude 10.4 is relatively faint. Brighter targets are easier. Atmospheric features can be subtle. Ground-based observations are affected by Earth's atmosphere. Preliminary observations have suggested hydrogen-helium atmosphere, expected for a gas giant, confirmed through general spectral properties. Possible sodium absorption. Some studies report tentative sodium detection, though requiring confirmation. Atmospheric opacity. Evidence suggests moderate hazes or clouds that partially mask molecular features. These observations indicate HAT P54b has a typical hot Jupiter atmosphere, hydrogen and helium dominated, with trace amounts of metals and molecules, and some level of atmospheric opacity from hazes or condensates. At 1,500 to 1,600 K, HAT P54b's atmosphere experiences supersonic winds, likely 2 to 4 km/s, redistributing heat from dayside to nightside. Day-night temperature contrast, probably hundreds of Kelvin despite wind redistribution. Vigorous convection, vertical mixing throughout the atmosphere. Complex chemistry, molecules forming and dissociating continuously. At these temperatures, clouds could form from silicate condensates, magnesium and iron silicates forming tiny droplets on the cooler night side, metal oxides, titanium oxide, aluminum oxide, corundum, essentially sapphire particles, photochemical hazes, UV radiation creating complex hydrocarbons and other molecules. HAT P54b appears to be a relatively typical hot Jupiter atmospherically, not extremely clear like some planets, showing strong molecular features, not heavily clouded like others with completely flat spectra, but somewhere in between with moderate opacity. Section 5. Scientific significance. What makes HAT P54b scientifically significant? Significance number 1. Ground-based survey success. HAT P54b demonstrates the continued value of ground-based surveys. While space missions like Kepler have revolutionized exoplanet science, ground-based projects like HATNet continue discovering planets around bright stars, the best targets for detailed follow-up. HATNet cost-effectiveness is remarkable. Total network cost, less than $1 million. Over 130 planets discovered. Cost per planet, less than $10,000. Compare that to space missions where discovery costs can exceed millions per planet. Ground-based surveys remain essential components of exoplanet research. Significance number 2. Sun-like star planets. HAT P54 is essentially identical to our Sun. Same mass, size, temperature. HAT P54b reveals how hot Jupiters behave around true solar analogs, directly informing our understanding of planetary systems generally. Our solar system doesn't have a hot Jupiter, but understanding how they form and evolve around sun-like stars helps us understand why our system's architecture differs, what conditions lead to different planetary configurations, how planetary migration operates around solar-type stars. Significance number 3. Population studies. HAT P54b contributes to hot Jupiter population statistics. With moderate inflation, density 0.45 g/cm superscript 3, moderate temperature 1,550 K, and moderate orbital distance 0.049 AU. It represents typical hot Jupiters, essential for understanding what's common versus rare. By studying many hot Jupiters like HAT P54b, scientists identify patterns. How does inflation correlate with stellar flux and temperature? What determines atmospheric opacity? How do formation mechanisms affect final properties? What fraction of hot Jupiters have various characteristics? Section 6. Future research. What's next for HAT P54b? James Webb Space Telescope. While HAT P54b might not be the highest priority JWST target, there are planets around brighter stars, it could be observed as part of broader hot Jupiter surveys. JWST could definitively detect molecular species, water, carbon monoxide, methane, measure atmospheric metallicity precisely, characterize cloud/haze properties, detect temperature inversions if present, observe phase curves revealing day-night temperature contrasts. JWST observations would answer, is HAT P54b's atmosphere enhanced in heavy elements, high metallicity? What causes the moderate atmospheric opacity, clouds, or hazes? How efficiently do winds redistribute heat? Does the atmosphere have a temperature inversion? High-resolution spectroscopy. Ground-based, extremely large telescopes, YELTs, coming online in the late 2020s will enable high-resolution spectroscopy, detecting individual molecular lines and measuring atmospheric dynamics. This could reveal wind speeds at different altitudes, atmospheric rotation patterns, day-night compositional differences, vertical atmospheric structure. Continued observations. Long-term monitoring might detect atmospheric variability, weather patterns, storm systems, orbital evolution, tidal decay causing orbital shrinkage, transit timing variations, indicating additional planets. Even without extensive individual observations, HAT P54b contributes to population surveys, characterizing many hot Jupiters to identify trends and test theories statistically. Conclusion. Let's recap what makes HAT P54b significant. 560 light-years away, HAT P54b continues its rapid orbit around a sun-like star. Every 3.8 days, another year passes on this gas giant world. One hemisphere baked by stellar radiation, the other cooled by darkness and winds. Supersonic atmospheric circulation, moderate inflation from stellar heating. A typical hot Jupiter teaching us about gas giant diversity. This planet represents something important: the power of persistent, well-designed ground-based surveys. HAT P54b wasn't discovered by a billion-dollar space mission. It was found by an automated network of small telescopes, each costing less than a nice car, operated by a dedicated team using clever design and systematic observation. The story of HAT P54b reminds us that exoplanet science isn't just about the biggest telescopes or the most expensive missions. Sometimes the most valuable contributions come from modest facilities operated with ingenuity, persistence, and smart strategy. HATNet has discovered over 130 exoplanets. Each one, whether extreme or typical, surprising or expected, expands our understanding of planetary diversity. And they did it with cameras you could hold in your hand, mounted on small telescopes, watching the sky night after night. Thank you for watching until the end. It truly means the world to me. If you enjoyed this video, please give it a like and hit that subscribe button for more cosmic adventures. I'd love to hear your thoughts. What was your favorite exoplanet we discussed today? And which one should I dive into next? Your suggestions help shape our journey together. I'll see you tomorrow for more explorations, and thanks again for tuning in.